Hello and welcome to this revision session for Paper 2 in AQA A-Level Physics. So in today's revision session we're going to look at how to answer examination questions on A-Level Physics Paper 2. So if we've been successful in this revision session we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you be carrying out this revision session? When completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and your answers to the question in the revision session. When you're doing this, make sure to write your answers in full sentences and show your full working out. Whilst in the right hand side, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session, and after the revision session write up these notes into a revision sheet for you to use independently. So how should you be revising A-Level Physics? So first step is to learn the key facts. So use revision guides, class workbooks, student prep notes and textbooks to learn key ideas of the course, which may include writing out notes yourself or making mind maps. The second step should be to test yourself. So use that Caboodle, Seneca, your own knowledge checkers to quickly test your own knowledge, and you may wish to do this with your own cue cards. Then the third step is to practice exam style questions. So use exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work, and you may wish to download your own examination past papers to do this. So the three steps of learning the key facts, testing yourself and practicing exam style questions are how you should be revising for your A-Level Physics. So let's now have a look at some questions on Physics Paper 2. So the first topic we're going to look at is gravitational fields. So the first question says comets are balls of rock and ice. Figure 12 shows a comet in an elliptical orbit around the Sun. The comet is closest to the Sun at point P. Table 1 shows the data for the comet at P. Show that the gravitational force of the Sun on the comet at P is approximately 3.9 times 10 to the 12 newtons. Then secondly, explain how the gravitational force and the data in Table 1 show that the comet is not in a circular orbit around the Sun. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, it's only one mark, so you see it's a very straightforward calculation. And we know that the equation to work out the gravitational force between two bodies is F equals Gm1 m2 over r squared. You then check all your values. Now you'll notice as well that the mass of the Sun is given to you in the equation book for the exam. Pop all the numbers in and you should get 3.88 times 10 to the 12 newtons. Now the second one is asking for you to comment if it's in a circular orbit or not. Now you've already done a topic on circular motion for paper 1, and you know the standard equation to work out the centripetal force for any object going in a circle. So you can have either F equals m omega squared r or F equals mv squared over r. Now you'll notice that table 1 gives you these, so you should be using the equation F equals mv squared over r. Work it out and you should indicate that the two forces are not the same, so therefore that tells us that the gravitational force is not acting as a centripetal force, so therefore it's not in a circular orbit. The next question says, the orbital period t of an object orbiting the Sun at a mean orbital radius r is approximately given by t squared equals kr cubed. Now the mean orbital radius of the comet is 18 re, where re is the mean orbital radius of the Earth. Estimate in years the orbital period t of the comet. Then the total energy of the comet is the sum of its kinetic energy and its gravitational potential energy. Show that the total energy of the comet at P is approximately minus 6 times 10 to the 21 joules. Then calculations for a different comet show that has a total energy of plus 6 times 10 to the 21 joules at its closest point to the Sun. A student suggests that the comet will not remain in orbit around the Sun. Discuss whether this suggestion is correct. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, as you know, you've got a constant there, so what you can do is remove the constant but say t squared equals r cubed for the comet and t squared equals r cubed for the Earth, and you can ratio them, and you can say t squared of the Earth over t squared of the comet is equal to r cubed of the Earth over r cubed of the comet. Now you have all those values because you know that the time in years for the Earth is 1, and because you using a ratio. You do not need to convert it into seconds. You know what the radius, or so the distance between the Earth and the Sun is, the radius of the Earth's orbit, because it's given to you in the equation book. And you also know the distance between the Sun and the comet. So with that, you can work out your value for time, t, and it is 76 years. Now in this next question, you've always got to remember that the total energy of a comet is its kinetic energy plus its gravitational potential energy. So you can work out the kinetic energy with a half mv squared, and the gravitational potential energy is minus gm1 m2 over r squared. Firstly, you can't use mg delta h because g is changing over the distances, so you can't use that. And remember, it's got to be a negative value because potential is considered to be a negative, as we'll get into in the next question. So you add the two, you work each one out, you add the two values together, and you should get approximately minus 6 times 10 to the 21 joules. Now, the next question, it's going to indicate that the comet will not remain in orbit around the Sun. Now, why is that? Well, like we said before, we always have gravitational potential energy as a negative value. The reason why that is the case is because we say that the gravitational potential energy at infinity, which is outside of the gravitational field, anywhere outside the field, is equal to 0. So this is telling us that if you have to have 0 energy, for gravitational potential energy to be outside the field, it has to be at 0. So if it's at plus 6 times 10 to the 21, it's above 0. So therefore it has more than enough energy to reach infinity and to escape the gravitational field, so it will not be in orbit around the object. The next question says, show that the total energy E of a satellite orbiting the moon is given by the equation E equals minus gmm over 2r, where small m is the mass of the satellite and big M is the mass of the moon and r is the orbital radius of the satellite. Then explain the significance of the negative sign in the equation before. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, once again, you've got to indicate that the total energy of an orbiting body is the gravitational potential energy and the kinetic energy. Now again, remember that the gravitational potential is a negative value, so you would have a half mv squared minus gmm over r squared. Now what you can then do is you can also rearrange this to equate the two, because one's a negative. So what you can therefore do is then rearrange your equation to have kinetic energy is a half mv squared, and it also equals gmm over r squared. So therefore we can just simplify it and say the kinetic energy is g big M small m over 2r. You can then add the gravitational potential energy to get the equation out as shown above. Now, what's the importance about the negative sign? Well, it's the idea that the satellite needs energy to get to infinity, and we set infinity to be 0. So if it's inside the gravitational field, if it's orbiting the body, it must have an energy less than 0. So it must be a minus. So remember again that the bound system, when it's in an orbit around a object, when it's in the gravitational field, it must have a negative value because it is attracted to another object. Or you could just talk about in terms of total kinetic energy, that the idea that the kinetic energy is going to be less than the negative gravitational potential energy. The next question says, the satellite has a mass of 1 times 10 to the 3 kilograms and orbits the moon in a circular orbit. The mass of the moon is 7.3 times 10 to the 22 kilograms. Determine the orbital speed of the satellite when the orbital radius is 1.95 times 10 to the 3 kilometers. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So what you've got to do is you've got to be aware of how you can work out orbital speed. Now you can work out the orbital speed by equating the equations of the centripetal force, okay, to the gravitational force and make V the subject, or you could just memorize the equation, which is V equals the square root of gm over r. Now remember, the escape velocity is square root of 2gm over r, so don't get those confused. You know the gravitational constant is given to you on the equation sheet. You've got big M, which is the mass of the object producing the gravitational field, which in this instance is the moon. You then divide it by the distance between the center of mass of the moon and the center of mass of the satellite. Remember, they give you that value in kilometers, so you convert that into meters by putting that times 10 to the 3 again, so it'll be 1.95 times 10 to the 6. Pop all the values in and you get 1.58 times 10 to the 3. The next question says the satellite's thrusters exert a force in the direction opposite to its direction of motion as shown in figure 5. This causes the radius of the orbit to decrease. Explain with reference to energy why the use of thrusters reduces the radius of the orbit, and then calculate the work done by the thrusters in reducing the radius of the satellite's orbit. Assume that the final orbit of the satellite is circular. So pause the video now, then unpause the video when you want to go through your answers. Right, so in answering this question you've got to pay very close attention. It says with reference to energy, so you can't be discussing about forces, because even if it's correct you won't get the full marks. So it's the idea that the thrust is in the opposite motion is opposite to the motion, so therefore work is being done on the object to reduce its gravitational potential energy. We then know from the gravitational potential energy that the value, that radius is in there, because it's minus gmm over r, so therefore it tells us that the thrusters will reduce the radius of the orbit. Now how do we then work out the work done? Well, we work out the difference in the total energy by doing the equation we had before, which gave us the total energy, which was minus gmm over 2r. You work it out in both places, so you work it out with r in those different values, you then subtract one from the other. Now remember, we're minus and a minus, so we're going to be getting a plus, so it's going to be 6.7 times 10 to the 7 joules. We're now going to look at some questions regarding electrical fields. So this question says electrostatic precipitators are used to remove smoke particles from the gases released by coal-fired power stations. Figure 5 shows a simplified electrostatic precipitator. A metal rod of radius A is placed along the vertical axis of a hollow metal cylinder of radius B. A point X is halfway between the rod and the cylinder wall. The rod and the cylinder are connected to a high voltage supply to create an electrical field inside the cylinder. The electrical field strength E is horizontal inside the cylinder. Gases containing smoke particles enter at the bottom of the cylinder. The smoke particles become charged and attracted to the cylinder wall. The smoke particles stick to the inside of the wall, and the gases leave at the top of the cylinder without the smoke particles. Figure 6 shows the variation of the magnitude of E with the radial distance r from the surface of the rod to the cylinder wall. The rod is at an electrical potential of minus 3.0 kilovolts and the cylinder is at 0 volts. A student suggests that potential at X is minus 1.5 kilovolts. Discuss this suggestion. So pause the video now, then unpause the video when you want to go through your answer. Now again, with these types of questions, they give you the graph in the question, so it's going to ask you to reference the graph in your answer. So it's the idea that the area between A to X is much larger than X to B, so what we're saying is it's not going to be directly proportional, it's not a straight line down, so this tells us that the electrical field is not going to be uniform. In fact, it's going to be more likely to be a radial field. So it indicates to us that the midpoint is not going to be halfway between the smallest and the largest value. It would be the case if it was a uniform field, but it wouldn't be because it's not acting as a uniform field. The next question says a smoke particle enters the cylinder near the rod. Initially it is uncharged and travels vertically with a velocity of 5.2 meters per second. Figure 7 shows the path of the smoke particle inside the cylinder. The mass of the particle is 2.7 times 10 to the minus 17 kilograms. The particle acquires a charge of minus 3.2 times 10 to the minus 19 coulombs near the rod. The particle experiences an initial horizontal acceleration of 91 meters per second squared due to the electrical field in the cylinder. Determine the magnitude of E at the point where the particle acquires the charge. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you'll notice straight away you've got a horizontal acceleration and you've got a mass. So the equation that sticks out to me is the equation F equals ma. So we can use F equals ma by multiplying 91 by 2.7 times 10 to the minus 17 kilograms. That then gives us our resultant force, and then we know that resultant force is the electrical field strength times by the charge. So as a result, we can then multiply by the charge given in the question, and we can work it out to be 7.7 times 10 to the 3 newtons per coulomb. The next question says the vertical component of the velocity of the particle remains constant at 5.2 meters per second. Assume that all of the forces on the particle are negligible except for the electrostatic force. State and explain any change to the magnitude and to the direction of the acceleration of the particle as it moves along its path. Refer to figure 6 in your answer. Then calculate the speed of the particle as it reaches the cylinder wall. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this first question? Well, it's asking about the idea to the change of the magnitude and the direction of the particle as it moves along the path. So when you're looking at figure 6, which was the graph, you've got to consider about the electrical field strength. Now, we've just looked at an equation which said F equals EQ. Now, from the graph, you'll have noticed that E gets smaller. It decreases in size, decreases in size, decreases in size, because it's most likely a radial field. So if E is decreasing in size, well, then the resultant force is decreasing in size, so therefore a resultant force causes acceleration, so the magnitude of the acceleration decreases. Now we'll notice that the direction of the acceleration hasn't changed. There's been no alteration to the direction of the force or to the electrical field strength's direction as such, so therefore the electrical field's direction, sorry, not the field strength but the field's direction, so therefore the direction doesn't change but the magnitude does. And so you can answer both of those points in that question. Now the next one, you're going to have to work out the speed of the particle. Now what you've got is, we know we've got the potential difference. How do we know that? It's from the diagram as shown, and we've got the charge from the previous question. So we know that the work done on the particle is going to be the potential difference multiplied by the charge, so 3 kilovolts or 3000 times by 3.2 times 10 to the minus 19. Now we know the initial kinetic energy of our particle is a half mv squared, and we can work that through to be 3.6 times 10 to the minus 16 joules. You can then add the work done because it's being accelerated, so therefore it's going to gain in kinetic energy. So you add the two together to get your total kinetic energy. Then what you can do is, now you've got your total kinetic energy by adding the two values together, and then you can work out V by doing kinetic energy is a half mv squared, rearrange it, make V the value, and work out your answer that way. We're now going to look at some questions regarding capacitance. So a student uses the circuit in figure 8 to determine the capacitance of a capacitor. The capacitor is initially uncharged. The variable resistor R is set to its maximum value and the switch is closed. R is then used to keep the charging current constant while the capacitor charges. The charging current is 0.3 milliamps, and during the experiment the student gradually decreased the resistance of R to maintain a constant current of 0.38 milliamps. The reading via the voltmeter is recorded every 10 seconds for 120 seconds. The time is measured using a stopwatch. The battery has an EMF of 6 volts and a negligible internal resistance. So calculate the maximum resistance of R, explain why the resistance of R needs to be decreased to maintain a constant current, and then show that the charge on the capacitor after 120 seconds is approximately 0.046 coulombs. So pause the video now, then unpause the video when you want to go through your answer. Once again, it's very important to note that all these questions are 1 mark only, so you're going to be using quite basic equations or quite simple statements in your answer. Now to work out resistance, we know resistance is V over I. Now we want the maximum resistance, and because we know current is a constant, it's 0.38 times 10 to the minus 3, because milli means 10 to the minus 3, we've got to use our maximum value of potential difference, which is going to be the EMF of the source, which is 6. So it's 6 over 3.8 times 10 to the minus 4, which is 1.6 times 10 to the 4. Now in our next question, it's the idea that the potential difference across the capacitor is increasing as it's charging, because it's building up that difference in charge across the both plates. So therefore the potential difference across the variable resistor is decreasing, so that will cause a current to go down, because you need that push, that potential difference, to push the charge across and to maintain that current. So therefore we're going to decrease the resistance to maintain that constant current. Now in this last one, we've been given the current and the time. So the obvious thing to work out is the charge by doing Q equals IT. We know that milli means 10 to the minus 3, so it's 3.8 times 10 to the minus 4 multiplied by 120 seconds to get 0.0456 coulombs. The next question says, figure 9 is a graph of the voltmeter readings V against time t. Determine the capacitance of the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, so how can you answer this particular question? Well, we know that capacitance is going to be Q over V, so you can't work it out from the gradient of the line, but what you can do is you can take values from the graph. So what you can do is take a reading from the graph to obtain the value of V after 120 seconds. So you're going to get between like 5.5 and 5.7 volts from how you've read that particular graph. You can then use the equation capacitance equals Q over V, and then we'll know what our charge is because we've just worked out in the previous question, divided by our value for V, and we get 8.1 times 10 to the minus 3 farads. The next question says the student makes a new capacitor as shown in figure 10. The two square metal plates have sides of length 15 centimeters. They overlap completely and are separated by a piece of dielectric material. The dielectric material has a thickness of 3.5 millimeters and completely fills the space between the plates. The capacitance of the capacitor is 0.13 nanofarads. Calculate the relative permittivity of the dielectric material and discuss whether the student could use the experimental procedure described previously to confirm the capacitance of the 0.139 nanofarad capacitor. So pause the video now and then unpause the video when you want to go through your answer. Right, so in this first question, we should be aware that to work out the relative permittivity of the dielectric material, we've got to use the parallel plate capacitor equation, which is C equals E0 ERA over D. So you can rearrange that to make E0 the subject, sorry, ER the subject, my apologies, by saying ER is equal to C times by D over E0 times by A. Now E0 is a constant given to you. You can work out the area by doing 15 times 10 to the minus 2 times by 15 times 10 to the minus 2 to work out your area. Remember again, you need to be converting from centimeters into meters. You can then also use the idea that the separation is 3.5 millimeters by having D is 3.5 times 10 to the minus 3 to get our answer out to be 2.3. Now you should have noticed for the question 6 that it's a nanofarad capacitor and the previous one was not a nanofarad, it was much higher capacitance. So what this tells us is that this new capacitor has a really much smaller capacitance than the previous capacitor. Now I like to visualize capacitors as holding like jugs of liquid, like jugs of water. So this particular capacitor is a much smaller jug. It can hold a lot less water, a lot less charge. Now charging a capacitor is like pouring water into a jug, so if we pour it at the same rate, it's going to fill up a lot faster, and most likely you're not going to get many measurements because the current would very quickly reach zero. It would become the capacity would be completely full of charge, okay, before you had to take your readings with every 10 seconds, so it just would not work. So the potential difference across the capacitor would reach 6 volts before you could take your readings with the stopwatch. We're now going to look at some questions regarding thermal physics. So the first question says figure 1 shows a boiling tube containing melted wax at 85 degrees Celsius. The boiling tube is in a beak with cold water. The temperature of the wax is recorded every minute for 16 minutes. Figure 2 shows the results. So estimate using figure 2 the melting point of the wax. Then the internal energy of the wax decreases at an average rate of 7.8 joules per second during the time the wax changes state. Estimate the mass of the wax in the boiling tube. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you should know that you change state, so the melting point will be when you have a straight line on a temperature time graph. So you look across and the straight line is occurring between about 80.2 to 80.4 degrees Celsius. When I say straight line, I mean flat line. Now the next one is we can now use this to work out the mass of the wax in the boiling tube, because the latent heat is the amount of energy per kilogram you need to melt it in this instance. So we can say that Q equals ml, and then we can also say E equals PT. Now we know what the power is because it gives you in the question, because joules per second is power, it's a watt. So you do 7.8 times by the time it needed to melt, so you can read it off the graph where it starts to have a flat line to when it finishes having a flat line. Convert that time back into seconds from minutes, and you can work out your value for your energy, which is Q. Then you can rearrange it, say M equals Q, which you've just worked out, over L, which you've just given, and then you get an answer between 0.022 to 0.025 kilograms. The next question says, describe how the average kinetic energy and the average potential energy for the wax particles changes between 8 and 16 minutes. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this one? Well, if you think when it's going from 8 minutes to 16 minutes, it's in the process of changing state, and then it decreases its temperature. So when it's changing state, the potential energy store of the object will decrease, because the state links into the potential energy store. So because it's changing state, and in this case it is melting, so therefore we're going to a substance which has particles further spread out, so the potential energy will go down. So the potential potential energy will decrease. The kinetic energy store is not linked to this because they are completely separate stores, so that stays the same. Now the temperature links to the kinetic energy store, so when the temperature is decreasing but the state is staying the same, well then the potential energy store will not change, but the kinetic energy store will go down because the object is decreasing in temperature. We're now going to have a look at some questions regarding magnetic fields. So figure 11 shows the path the proton takes as it travels in the Earth's magnetic field. The proton moves in a helix around the magnetic field line. The radius of the path is shown in figure 11 and the proton moves with a constant speed. The magnetic flux density in this region is 1.2 times 10 to the minus 7 teslas, and the velocity of the proton has two components of constant magnitude. The component perpendicular to the mag field is 450 kilometers per second, and the component parallel to the mag field is 120 kilometers per second. So the solar wind is a stream of highly energetic particles, such as protons that flow out from the sun. So state the condition in which a charged particle moves in the magnetic field and experiences no force. The radius r is constant and calculate r. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? So how do you know it's experiencing no force? Well, in a magnetic field, a charged particle experiences no force if either it is stationary or it's moving parallel to the field line. So it must be, because it's moving, must be moving parallel to the field line. Now, work out the value of R. Well, straight away you know you've got B, you've got Q, and you've got V. So you can work out what the force is by doing F equals BQV. Now importantly, what value are we using for V? Well, we're not going to be using the value parallel to the magnetic field because that will not be relevant in this case. So you've got to use the perpendicular velocity, which if you can see on here is 450 kilometers per second. We don't work in kilometers per second in physics, we work in meters per second, so we convert that to 4.5 times 10 to the 5 meters per second. That allows us to work out F, and we know that it's moving in a circular path. So because we know it's moving in a circular path, as we can see here, it's moving in a helix, we can use the centripetal force equation of mv squared over r. We're linking our two topics together. We've got the mass, we've got the force, we've got the radius of the orbit, so therefore we've got the speed, so we can work out the radius of the orbit to be 3.9 times 10 to the 4 meters. The next question says, explain why the proton takes the path as shown in figure 11. Then the interaction between the solar wind and the Earth's magnetic field can cause a small change in the magnetic flux density near the Earth's surface. Explain how this small change can cause the induction of very large voltages in power transmission lines. Refer to Faraday's law in your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? So like we mentioned before, it's very important to note that the parallel component of the velocity is unaffected by the magnetic field because it works perpendicular to the velocity. So the magnetic force is the centripetal force, and the centripetal force will always act perpendicular to the motion of the object. So therefore the centripetal force will cause the circular motion. Now in the second question, it's so important you actually reference Faraday's law. So what is Faraday's law? It's that the EMF is directly proportional to the rate of change of magnetic flux linkage. So we must be achieving a high EMF, because it indicates that in the question of an induction of a very large voltage. So that can only be achieved by a very, very big change in the rate of flux linkage. So that happens because you've got a very large area, because we know flux linkage links into the magnetic field strength and it links into the area of the object because our power cables are so long, as indicated in the question. The next question says, describe what is necessary for a charged particle to experience a force due to its movement in a magnetic field. Then show the radius of a circular path of a charged particle in a uniform magnetic field in a vacuum is given by the equation R equals P over BQ, where P is the momentum of the particle, B is the magnetic flux density, and Q is the charge of the particle. So pause the video now, then unpause the video when you want to go through your answer. Right, for this first one, you've got to just remember this key idea, and it experiences a force when it has a component of its velocity perpendicular to the field. So it's important to note that the velocity and the magnetic field are perpendicular to each other. If it was parallel, it would experience zero force completely. Now, how do you do the second question? Well, what you do is you remember that the magnetic force here, which is F equals BQV, is going to therefore be equivalent equating to the centripetal force because it's causing the object to move in a circular path. So we can say mv squared over r equals bqv. We can then rearrange that, make r the subject. Remember that momentum is mass times velocity, so p equals mv, and we get our answer out to be r equals p over bq. The next question says a cloud chamber is a particle detector that produces visible tracks. The tracks form as charged particles ionize air molecules along their paths. Charged particles produce spiral tracks when the cloud chamber is placed in a uniform magnetic field. Figure 11 is a full-size image showing the track of a particle created at point X in a cloud chamber. The particle travels in a horizontal plane and the magnetic field direction is into the plane of the page. Explain why the radius of the path decreases as the particle created at X travels through the cloud chamber. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? So it's important to note that as it's going through the cloud chamber, it's colliding with the particles in the chamber. So therefore, it's going to lose some of its kinetic energy as it whacks into them. Now, the particle's velocity will therefore decrease, its momentum will decrease. And we've just looked at our previous equation that says R equals P over mv. So that tells us, when you work it through, not R equals P over mv, if you look at the previous question, R equals mv over bq. So R equals P over bq. So what that indicates to us is that the radius of the orbit is directly proportional to the velocity and the momentum. So therefore, if the momentum decreases and if the velocity decreases, well, therefore the radius will decrease as well, showing the path in the figure. The next question says, a gamma photon produces two particles in a pair production event in the cloud chamber. Figure 12 shows the tracks due to the pair production event. Explain what figure 12 indicates about the three particles involved in the pair production event. So pause the video now, then unpause the video when you want to go through your answer. Right, it's a very common question to link magnetic fields and particles, because that's how particles were first discovered and understood in the 1950s to 1960s. So because our particles have spirals in opposite directions, that tells us straight away that the charges of the two particles produced in the pair production event are opposite because their spirals are in opposite directions. But they must have the same momentum, so most likely the same mass and the same velocity, but just in opposite directions, because the tracks have a similar radii. So therefore we know that R equals mv over bq. So if R is the same, mv must be the same. Now finally, if you look on this picture, you'll notice that there's no track before the event takes place. Now you should remember from paper 1 that pair production is when a photon is then changed into a particle-antiparticle pair. Now that indicates to us that if there's no track beforehand, well then the photon beforehand, which must be present for a pair production event, must be very weakly ionizing or very difficult to detect because there is nothing there in the chamber. There is no track. Let's now have a look at some questions on nuclear physics. So the first question says FDG is a chemical used in medicine. FDG contains the nuclide fluoride 18. Fluoride 18 has a half-life of 6.59 times 10 to the 3 seconds. First, you state what is meant by the half-life of fluorine 18. Then show that the decay constant of fluorine 18 is approximately 1.1 times 10 to the minus 4 seconds. Then a sample of FDG with an activity of 370 megabecquerels is injected into a patient. Assume that the activity of the sample is due only to fluorine 18. Calculating kilograms, the mass of fluorine 18 in the FDG sample. Then the sample of FDG was produced in 12 hours before it was used in the injection. Calculate the activity of fluorine 18 in the sample of FDG when it was produced. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you've got to know what the definition of half-life is. And the half-life is the time taken for the activity or the mass or the number of radioactive nuclei in the sample to halve or decrease by 50%. Now again, this next question is 1 mark, so you know it's going to be a very simple equation. So you know that the half-life is log 2 over the decay constant, so decay constant is log 2 over the half-life, so therefore you can pop it through and your work out your answer to be 1.05 times 10 to the minus 4. Now in this next question, it's a bit more challenging. Now we know we've been given the activity, and we know activity is equal to lambda n. Now we've just in the previous question worked out lambda, the decay constant, so therefore we can work out n. Now remember, 370 becquerels for the activity is 370 times 10 to the 6, because that's what mega means. So we can then use that value to work out n, which is 3.52 times 10 to the 12. That's how many particles that you have. So therefore you can then work out, okay, the mass in total by doing the n times by the atomic mass divided by Avogadro's constant. Now you know that the mass of 1 mole of fluorine is 1.8 times 10 to the minus 2 kilograms. So if you know how many particles there are, you can then work out how many moles you've got by dividing that value by Avogadro's constant, because it is how many particles are in 1 mole. And then when you know your number of moles, you can multiply by the number on the screen, 1.8 times 10 to the minus 2 kilograms, to get your total mass to be 1.1 times 10 to the minus 13 kilograms. Now in this last question, we've got a time and we've got an activity, and we want to work out our initial activity. So we say A equals A0 e to the minus lambda t. Remember, t has to be in seconds now, so 12 hours will have to be converted into seconds by doing 12 times by 60 times by 60. And then what we can do is make A0 the subject, A0 being the activity at the start. So we can say A0 is going to equal A over e to the power minus lambda t. We've got lambda, the decay constant, in the previous question. We know what our value of A is 370 times 10 to the 6. We can pop our values in and we get 3.5 times 10 to the 10 becquerels. The next question says, state and explain one practical problem in achieving fusion in reactors. The equation below describes a fusion reaction that occurs in the Sun, and table 2 shows the mass of each nuclide. Calculate in joules the energy released in this reaction. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you've got to realise there are 3 problems with fusion in nuclear reactors on Earth currently. Firstly, you could indicate that it's difficult to achieve the high enough temperatures and pressures in the plasma to constantly have fusion working at a consistent rate. Secondly, you could indicate that extracting the energy from the plasma after it's being produced is a very cost-effective process. Is not a cost-effective process, sorry, and actually you don't have an energy surplus after this. You actually have an energy deficit. And then finally, the idea that neutrons are produced in this fusion process and they've got a high energy, so are likely to be ionizing, which will be an issue. Now in this next question, we want to use our equation delta E, the energy difference, the energy released, is equal to delta M, the change in mass in before and after the reaction, times by C squared. So what you do is you work out your total mass before by adding the mass of 3 helium plus 4 helium. You then find the mass of the beryllium afterwards to find the mass afterwards. You then calculate your mass difference. You then multiply it by C squared to get your energy in joules, and you should be getting 2.6 times 10 to the minus 13 joules. The next question says, uranium fuel rods used in a thermonuclear reactor contain uranium-238 and uranium-235. Table 3 gives the mass of a uranium-238 nuclide and a uranium-237 nuclide. Deduce whether a uranium-238 nucleus can decay into a uranium-237 nucleus and a neutron. Then describe how a chain reaction occurs in the uranium-235 fuel. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you've got to understand that a decay process, you have to lose mass ultimately, because some mass is converted into energy. So you find the mass between the 238 uranium, and then the mass of the 237 uranium plus the mass of the neutron is given to you on the equation sheet. And then you notice that the decay cannot happen because actually the 237 uranium plus a neutron has a higher mass than the uranium 238. So therefore that decay cannot take place. Now the second question is explaining how a chain reaction occurs. Now the important thing to note is you've got to be aware that a chain reaction is caused by a neutron being absorbed by a uranium nucleus and causing fission from that process. Now it's only the uranium-235 that can absorb this neutron and then cause fission, and then the fission process itself will produce more neutrons, between 2 and 3 for every nucleus, which will then go on to fission other nuclei. The next question says, state one substance that is used as a moderator in a thermal nuclear reactor. The neutrons required to produce fission in many reactors are thermal neutrons. State why they are called thermal neutrons. Then explain why the kinetic energy of the neutrons needs to be reduced for the chain reaction to occur. And neutrons lose kinetic energy by a series of collisions with nuclei of the moderator. Each neutron keeps an average of 84% of its incident kinetic energy in each collision. One neutron has an initial kinetic energy of 2 times 10 to the 6 eV. To deduce the average number of collisions the neutron makes to reduce its kinetic energy to 2.5 times 10 to the minus 2 eV. So pause the video now, then unpause the video when you want to go through your answer. Right, in the first one, it's just a fact you've got to learn. Either water or graphite, both of those are used as moderators in nuclear power stations in the UK. Now we call these neutrons in the process thermal neutrons because they have collided with the fission products and removed energy, kinetic energy from those products. So ultimately after the collisions they're in thermal equilibrium with the fuel and the moderator because they have collided so many times they have the same amount of kinetic energy. Now why does kinetic energy need to be reduced? Well, it's the idea that we need the neutrons produced in the fission process to cause fission in other nuclei, okay, and at least more than one in each event does that. Now the idea that it will be the neutron will be accepted by the nucleus depends on its kinetic energy. So the faster neutrons are less likely to be absorbed and therefore by the uranium-235 nuclei and to therefore induce fission. So reducing the kinetic energy increases the probability of acceptance into the nucleus and fission being taken out place. Now this last question, question 6, is all about mathematics. Now when you're losing a percentage or keeping a percentage of energy in each collision, you can work it out by multiplying the value you're keeping it by the number of collisions. So in this case it's 84%, so it's 0.84. So you can see we're multiplying the value by 0.84 to the power of n. So we can say the final value is equal to the initial times by the percentage kept times to the power of the number of collisions. So it's 2.5 times 10 to the minus 2 equals 2 times 10 to the 6 times by 0.84 n. We can then rearrange it, make n the subject. Remember, if you've got exponentials you can use logs when you're rearranging that to get 105 out. Now the next question says, liquid sodium is used as a coolant in some types of nuclear reactor. Table 4 gives some properties of sodium. Now calculate the energy required to heat 3.3 times 10 to the 5 kilograms of sodium from an initial temperature of 20 degrees to a final temperature of 560 degrees Celsius. And then during the operation of the reactor, radioactive cesium-137 is produced. The cesium-137 is removed from the reactor as waste which needs to be stored. Cesium-137 decays into stable barium-137 with the emission of a beta particle and gamma radiation. The half-life of cesium-137 is 30 years. Outline the problems associated with the storage of this waste. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question you're given lots of information, but what stands out to me is that you've got the average heat capacity of the solid and the average heat capacity of the liquid and the latent heat of fusion. So it's important you have to work out the energy required to heat it up from 20 to 98 degrees, and that's going to be the average heat capacity of the solid multiplied by the mass, which we're given to be 3.3 times 10 to the 5, multiplied by the change in temperature, so 98 minus 20. That gives us that energy. We can then work out the energy when it's changing state by saying E equals ml. We've got the latent heat of fusion. Now be careful in all these values, by the way, they give you the kilojoules, so you need to convert the latent heat and all the heat capacities into joules by multiplying by 10 to the 3. So you multiply the mass by the latent heat of fusion, and then finally do the heat capacity when it's a liquid, so do MC triangle T, which is going to be from 98 to 560. And then doing it by the heat capacity of the liquid. So when you do all those values, you work them all out, you then got to add them all together because we're working out the total energy. So you work out all three and you get 3.09 times 10 to the 10, 1.98 times 10 to the 11, and 3.63 times 10 to the 10. Add them all together to get 2.65 times 10 to the 11 joules. Now in this last question, you've you will be tested or asked to know about how you can store nuclear waste. So from looking at the information given in the question, you've got to link to the idea that there's going to be high energy particles released, which could be ionizing. So you've got to think about how you can shield the radiation so it doesn't release these particles around people. So you can think of having like a shield, like a steel or lead or very thick concrete wall, and also you could have maybe possibly being in water to shield it and also to cool it. The other idea is that the half-life of cesium is 30 years, so you'll need to store it for a very long time. Now the general rule in radioactivity is to store it for at least 5 half-lives, so it's down to a very small percentage of its initial value. So you'd say you'd have to store it for at least 150 years because one half-life is 30 years. So if you've been successful and you've learned in this revision session, you should be able to answer A-level physics examination style questions for physics paper 2, assess your understanding on A-level physics and understand what topics you need to improve upon for AQA A-level physics. So thank you very much for watching this revision session on paper 2 for AQA A-level physics. Thank you very much and have a lovely day. Hello and welcome to this revision session for AQA A-level physics on paper 2. So in today's revision session we're going to be looking at how to answer examination questions on A-level physics paper 2. So if we are successful and we learn in today's lesson, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics and understand what topics we need to improve upon for A-level physics. So how should you prepare for this revision? So when completing your work in this revision session, divide your piece of paper into 2 sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the question in the revision session. When you're doing this, make sure to write your answers in full sentences and show your full working out, whilst in the right hand side write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. At the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising A-level physics? So the first step is learning the key facts, understanding the knowledge of the course. So use your revision guides, class workbook, prep notes and textbook to learn the key ideas of the course, and you may wish to make mind maps or write out notes yourself. The second stage should be retrieval, testing yourself. So use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. And then finally, the last step is to practice examination style questions. So use exam prep books, homework books, supervised study books and additional workbooks to answer exam questions and mark your own work, and you may wish to download your own past papers to do this. So the 3 steps of learning the key facts, then testing yourself and then practicing exam style questions are how you should be revising A-level physics. So let's now have a look at answering some questions on the topics on paper 2 in A-level physics. So the first questions are going to be on gravitational fields. So the following question says, the lines in figure 4 show the shape of a gravitational field around 2 stars, G and H. Compare with reference to figure 4 the masses of G and H, and then X and Y are 2 points in the field. Annotate figure 4 to show the field direction at X and the field direction at Y. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you've got to remember that in a field that the density of the field lines indicates the strength of the force, and in this case the gravitational force is affected predominantly by the mass of the object that is present. So you can see that G must have a greater mass than H does, and why is that? Because there's 2 things you could possibly say. You could possibly indicate that the density of the field lines is greater around G compared to H, or you could say that the null point, the point at which the 2 gravitational fields will cancel each other out, is closer to G than it is closer to H than it is to G, so therefore G must have a stronger field than H. Now again, the other fact you've got to remember about gravitational fields is that the field lines point in the direction a point mass would take. So therefore, for both of them, it would indicate towards the actual object, because it's a gravitational field. It's always an attractive force that's going on for gravity, so therefore the masses will always be going towards the two objects, so therefore the field line should be pointed towards the actual object, and it's important that they're given tangential arrows as well. Now the next question says, a spherical asteroid P has a mass of 2 × 10 to the 20 kilograms. The gravitational field strength at its surface is 0.40 newtons per kilogram. Calculate the radius r of P. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, if you look at your equation sheet given for your examination, you are aware that you can work out the gravitational field strength little g by doing little g equals big G m over r squared. So we can therefore rearrange this and make r the subject by saying r is equal to the square root of gm over g. You've then got the value of the gravitational constant from your equation sheet, you've got the value of the mass in the question, and you've got the gravitational field strength little g in the question as well. So you pop in all the values, you work it through, and you get 1.8 times 10 to the 5 meters. The next question says, sketch on figure 5 the variation of the gravitational field strength G with distance r. The distance r is measured from the centre of P, and then explain what is represented by the area under the graph between r equals r and r equals 2r on figure 5. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, it's important to note that you should be aware that for these objects that the gravitational field strength will vary as a radial field, so therefore it's going to be sketching across like so. Now again, you'll be aware that as the distance doubles, well therefore the field strength is going to go down by a factor of 4 because it's related to r squared. So when one is double, the other is gone by the power of 4. Now we know that at a distance of r that the field strength is 0.40 from the previous question, so therefore at 2r it's going to be 0.4 divided by 4, so it's 0.1, and then you can do for 3r, so then you can divide that by a factor of 4 as well, okay, so you can work it through like so. Sorry, that would be for 4r. For 3r, what you would do is you go from r to 3r, you then go by a factor of 9 because there's 3 squared, so it'll be 0.4 divided by 9, which is 0.044. So you can plot those points in there and sketch the line in. Now, what is represented by the area? Well, again, there's a couple of answers you could say. So you've got to be aware that in these graphs that the area under the line represents the energy transferred or the work done per unit mass, or that is, in essence, the gravitational potential. So therefore, if we can think it in terms of energy per unit mass, it's the energy transferred or work done on an object per unit mass to move from r to 2r, or you could say it's the increase in gravitational potential moving from r to 2r. Again, remember how to work out values from graphs. The next question says, asteroid P approaches the two stars G and H. Figure 6 shows one position of P close to H. The gravitational force on P from G is 6.38 times 10 to the 12 newtons. The mass of H is 3.00 times 10 to the 25 kilograms, and the mass of P is 2.00 times 10 to the 20 kilograms. The distance HP is 1.50 times 10 to the 11 meters. Calculate the magnitude of acceleration of P. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, you know straight away that it's worth 4 marks. It's going to be either a double step calculation or a challenging calculation that you're given. Now you have the gravitational force, you have the mass of two objects, and you have the distance between the two. So what you can therefore do straight away is say F equals gmm over r squared. So what you can then do is work out that value of the force. So you can find the force between P and H. So therefore you can say, well, the force between P and H is 6.67 times 10 to the minus 11 times by 3 times 10 to the 25 times by 2 times 10 to the 20 all over 1.5 times 10 to the 11 squared. So therefore gives you an answer of 1.8 times 10 to the 13 newtons. So what we've got here is we've now got the two components of the gravitational force, the one from P to G and the one from P to H. So as a result, we can work out the total by using a bit of Pythagoras Pythagoras in saying that the total is going to be FPH squared plus FPG squared, all square rooted. So we do those two and we square both values, add them and square root them to get the total value of F to be 1.9 times 10 to the 13. At that point we know acceleration. Well, we've got the masses, we know the force, so we therefore know acceleration is the overall force divided by the mass. We've just worked out the overall force to be 1.9 times 10 to 13. We can then divide it by the mass, which is 2 times 10 to the 20, to get our answer to be 9.4 or 9.5 times 10 to the minus 8 meters per second squared. We're now going to have a look at some questions to do with the electrical fields topic. So figure 7 shows two identical negative point charges, QA and QB, in fixed positions 8 millimeters apart. O is a point midway between the charges, P is a point 3 millimeters away from O, and equidistant between QA and QB. Firstly, the resultant electrical field strength at P is 1400 newtons per coulomb and towards O. Calculate the charge of QA. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, a couple of things. Firstly, what do we know that the equation is for the resultant electrical field strength? Well, we know from the equation sheet that E is equal to Q over 4 pi epsilon 0 R squared. But what we also know is from our setup, from our diagram, we can also say that the resultant electrical field strength is going to equal 2E cos theta. So what we can do is we can work out what E is going to be by using that equation of Q over 4 pi epsilon 0 R squared. We can then link that into we can work out from the equation of E resultant is equal to 2E cos theta. We can therefore link that into work out E, and therefore what we can do is we can then work out one of the charges by using that equation E equals Q over 4 pi epsilon 0 R squared to work out our value. So you can work that all through using trigonometry to work out what cos theta is going to be, and then you can work it out and you get Q equals 3.2 minus 3.2 times 10 to the minus 12 coulombs. The next question says, sketch on figure 8 the variation of electrical potential V with displacement x from O between QA and QB. Calculations and numerical values of V are not required. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to be aware that the electrical potential will always be a negative value, and that's a very important idea because they're attracting each other. So at that point we know it's going to be a negative value. So at that point there's going to be a smooth curve, which is always negative, and there's going to be a non-zero maximum at the y-axis, and it's going to be asymptotic at about 4 and minus 4. The next question says, figure 9 shows a point R between O and QB. QA and QB are fixed positions. A small mass M with a negative charge Q is released from rest at R. Only electrostatic forces act on M. After release, M oscillates about O along the line between QA and QB. State and explain how the direction of the resultant force on M varies during oscillation. Describe the energy changes of M from its release until it reaches O for the first time, and then deduce whether or not M performs simple harmonic motion. So pause the video now, then unpause the video when you want to go through your answer. Right, so this question is a very standard question for paper 2 because it links two topics together, the electrical field strength and simple harmonic motion. So you should know for the first one, state and explain how the direction of the resultant force on M varies with the oscillation. Well, the direction is always acting towards O. That's because the idea that the Q charges will both repel M, and therefore the nearer it is to Q will repel more, so therefore it will always be attracted to O. Now, in terms of what's happening, it's going from electrical potential energy because it's moving due to the repulsion in the charges. Okay, so it's transferring to kinetic energy because it's now moving due to this repulsion. Now, again, to get that second mark, you've always got to indicate how the energy changes will take place. So a decrease in electrical potential energy will be equal to an increase in the kinetic energy. So when it goes from one store, it will go towards the other store. Now the last one, will it perform simple harmonic motion? Well, this is actually a link to the idea of what simple harmonic motion is. So simple harmonic motion comes from the idea that the acceleration is directly proportional to the displacement in the opposite direction. Now you should know that the electrical field strength and the electrical force will link as 1 over r squared. So therefore it's not going to be directly proportional to distance because it's over distance squared, so therefore it will not be simple harmonic motion. We're now going to look at questions on the capacitance topic. So the first question says, state what is meant by a capacitance of 37 millifarads. Then a capacitor is made up of two parallel metal plates which are separated in air by a distance d. A cell of negligible internal resistance is connected across the capacitor as shown in figure 10. Switch S is closed and the capacitor becomes fully charged. While S is still closed, the plate separation is reduced to d over 2. State and explain what happens to the magnitude of the charge stored by the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, this first question, you've got to learn how to just define what we mean by capacitance. So capacitance is the charge stored per unit volt. Now in this case it's 37 millifarads, so therefore it's 37 millicoulombs stored per unit volt, or per 1 volt. Now in the next question, what's going to happen to the magnitude of charge stored by the capacitor? Now again, you've got to link it to the equation. Now the equation for capacitance is that capacitance is going to be equal for a parallel plate capacitor to E0 ER A over D. Now again, we can consider E0 and ER to be the same value in this instance because we're not changing any of those terms, so therefore capacitance is going to be linked to A over D. Now again, we know that Q is equal to CV, so we know straight away that the capacitance has doubled. We know that the potential difference or the voltage has stayed the same. We're told that from the question. So therefore, Q must have to double because we're linking it into therefore that separation. You can see how they all link together in their different equations. Now the next question says, explain how charge is conserved when the plate separation is reduced. S is now opened. The plate separation is increased to D. And state and explain how the energy stored in the capacitor changes during this process. And then explain how energy is conserved when the plate separation is increased as described in the previous question. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So, in this first question, you've got to understand that charge is conserved because there's an equal number of electrons removed from the positive plate as deposited onto the negative plate. Remember the idea that there's always two plates. One is where the electrons are removed, okay, and they are the ones from the positive plate, and the electrons are going onto that negative plate. Now, what's going to happen in the next question? So again, what will we do? Well, we know again that charge is going to stay the same because the capacitor is isolated, or that the charge can't flow because the switch is now open, so the charge can't flow around the circuit. So at that point, it tells us that the capacitor halves because we know that the capacitance halves because you know E equals Q squared over 2C. So therefore, at that point, we can tell that energy doubles. So you can even say this qualitatively, but you can't get enough marks for this. The idea that work has to be done to that external system, to the capacitor, to separate out that plus and minus plates. So therefore, energy must be stored in the capacitor because we're putting energy into it to actually separate those two plates out. So we know that from the previous one that links into the equations. Now, how is energy going to be conserved? Well, the idea of energy is conserved because the gain in stored energy is provided by work being put into the capacitor to separate the plates apart. So work is being put in, energy is being put in to that capacitor to actually physically separate those two plates from each other because they are attracting each other. Let's now have a few questions on thermal physics. So, the first question says, the volume of a fixed mass of gas is kept constant. Explain why the pressure of the gas decreases when the temperature is decreased. Then, show that the pressure P of an ideal gas can be given with the equation P equals rho RT over M, where rho is the density, T is the absolute temperature, and M is the molar mass of the gas. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So you've got to talk very qualitatively about what is going on. So the idea is that if we decrease the temperature, the internal energy of the gas will decrease, because for a gas, that the internal energy for an ideal gas is the thermal energy. It is linked to the temperature. So therefore, what we can say is that the mean kinetic energy, or the speed of the particles, will decrease. So therefore, if the particles are moving slower, the frequency of the collisions with the container, okay, now remember, it's the frequency of the collisions, not just the collisions themselves, the frequency of the collisions will therefore decrease. So therefore the change of momentum that's occurring will decrease, and we know that that force is equal to change in momentum over time. So therefore, if the change in momentum decreases, the force exerted will decrease. So therefore the pressure will decrease, because we know pressure is force over area. The area is unchanged, the force is reduced, the pressure goes down. Now the next question links to a lot of the previous equations you know for thermal physics. So we know that the number of moles is equal to M over M. We know that rho is equal to M over V, and we know that PV equals nRT. So what you need to be able to do is link those into the equation. So what you can do is start with PV equals nRT. We can then sub in M over M for N, or we can sub in that V is going to equal M over rho. The two small m's will cancel through. We've then got the big M left in the equation. As you can see, we've got rho left in the equation. We can rearrange to make P the subject, and we get out our value. The next question says, figure 3 shows the variation of pressure with temperature for a gas at a constant volume. The density of the gas is 1.6 kilograms per meter cubed, and assume that the gas is ideal. Determine in kilograms per mole the molar mass of the gas. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you consider answering this particular question? Well, when you're given a graph, you've got to be able to use it. So use a data point from the line of best fit, which is linking, as you can see, the pressure and the temperature. But you'll notice from the equation given, from the graph given, that the pressure is in megapascals, so you have to convert that, and the temperature is in degrees Celsius. Now, the ideal gas equation needs the absolute temperature, so you need to convert from degrees Celsius into Kelvin. So what you'll do is you'll convert the temperature into Kelvin. You'll convert the pressure into pascals. We'll then use our previous equation of P equals rho RT over M. We know R from the equation sheet, because it is just a gas constant. We know rho from the information given in the question. You are told it. We've read off T and M from the graph, and therefore we can work it out to be 3.9 times 10 to the minus 2. Another way in which you can do it is you can determine the gradient of your graph, and you'll be aware that the gradient is going to be equal to rho R over M, because we know that it's pressure over temperature, which from the previous equation we can work it through. So we can then use that to work out what our value of kilograms per mole is going to be. Let's now have a look at some questions on the topic of magnetic fields. So the first question says, a student investigates the EMF induced in a coil of wire when it is rotated at a constant angular speed in a uniform magnetic field. An oscilloscope is connected across the output of the coil. Figure 1 shows the trace on the oscilloscope screen, and figure 2 shows the time-based setting for the oscilloscope. Firstly, describe what the student should do to determine an accurate value for peak EMF induced in the coil. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important you understand how to work out values accurately from an oscilloscope. So what you're firstly going to have to do is work out what the number of each vertical square means in terms of volts. So you can look on the right hand side, and you can see that is in fact for the time base, so that's not going to be relevant in this case. However, what we can do is we can work out what the value is by looking at what our Y gain is going to be, our Y scale. Then what we can do is turn off the time base, and then what you can do is increase the Y gain or decrease like the volts per division setting, the Y gain, so the trace takes up more of the screen, so it's easier to read off the value. At that point you want to work out the most accurate value. Now in science, in physics, to reduce your percentage uncertainty, to increase the accuracy, you want to take the largest value possible, and that reduces that value. So as a result, the largest value possible is not the peak voltage, but in fact it's the peak to peak voltage, the value from the top of the line to the bottom of the line. So you'd work out your peak to peak voltage and then divide by 2 to get that most accurate value. The next question says, show that the angular speed of the coil is approximately 13 radians per second using figure 1 and figure 2, and then figure 3 shows the oscilloscope screen with the time base set to off. The student wishes to make an accurate measurement of the time period of the induced EMF. Calculate an appropriate time base setting and explain your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So how to work out the angular speed is you work out the number of squares for the multiple cycles, and then what you can do is you can therefore work out like 9.6 to 10 squares for 4 cycles. So therefore what we can do is work out the number of squares for 1 cycle. We can then work through by saying that the angular speed is 2 pi over t. So therefore we know 2 pi because it's just a number. We know t because we can work it out from the previous question, because we can work out the time needed for 1 period. Okay, again, it's more accurate to take multiple values and then divide by the number of values that you take to reduce your percentage uncertainty. So you should get an answer from about 12.7 to about 13.1 radians per second. Now again, the answer for this next one should be about 50 milliseconds per division, because what you want is you want your 1 cycle to fill the entire screen. So you've got to think, how would you work it through to get 1 cycle in there? So it's going to be that 50 milliseconds value from the information given in the previous question. The next question says, the peak EMF is 7.5 times 10 to the minus 2 volts. The coil has an area of 6.0 times 10 to the minus 3 meters squared and 25 turns of wire. Calculate the magnetic flux density of the magnetic field. And figure 4 shows the coil connected to a 27 ohm resistor. The resistance of the rest of the circuit is negligible. Calculate the mean power dissipated in the resistor. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you should know from the equation sheet that the maximum induced EMF, the peak EMF, is equal to BAN omega. Now in the previous question we just worked out omega. You have got the value of area in the question and the value of N. So at that point we have peak EMF, we have A, we have N, we have the angular speed, so you can work out what B is, and we get 0.039 Teslas. Now in this next question again, what are we aware of? We've got the resistance, we know it's 27 ohms. Okay, and what we also know is we can actually work out what our value of V is. But because it's an AC generator, you've got to remember, or an AC motor, what you've got to remember is you've got to be using the value of VRMS, because you use VRMS and IRMS to work out values in alternating current circuits. So the first thing to do is work out VRMS. Now we have peak EMF or V0, so we can say VRMS is V0 over square root 2. That's again an equation given to you on the equation sheet, and at that point we can sub that into the next equation of P equals V squared over R. We've got R, we've just worked out V, so it's 1.0 times 10 to the minus 4 watts. So now what we're going to do is we're going to look at answering questions on nuclear physics. So the first question we're now going to look at is that a proton of 0.675 MeV of kinetic energy collides and fuses with a stationary nucleus of boron-11. An excited carbon-12 nucleus is produced. The excited carbon-12 nucleus de-excites to a stable carbon-12 nucleus by emitting a gamma photon. Calculate in MeV the energy of this gamma photon. Assume the carbon nucleus does not recoil when the gamma ray is emitted, and state your answer to the appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So the first thing to note is you can see that from our equation we've got a proton and we've got the boron, and that then turns into the carbon nucleus, or the carbon-12 nucleus. Okay, so the first thing we need to do is add the proton rest mass to the mass of the boron, and at that point we can work out what our mass defect is, or the difference in the masses between that and carbon-12, and then at that point we can then multiply our rest mass, or the mass defect, which we have probably in U, by 931.5 MeV. Again, that's a conversion factor. You've just got to learn how to convert between U and MeV, which is by multiplying by 931.5, and at that point we've got our energy in MeV. We can then add the kinetic energy contribution by the proton, which we're told in the question is 0.675. So at that point we get 16.6 MeV, and again we give our answer to three significant figures. Why is that? Because if you look in the question, the number of significant figures given for energy in this question is 3, because it's 0.675. so we give our answer to the same number of significant figures as the value given in the question, which is 3, so therefore it is 16.6 MeV. The next question says, an alternative mode of decay for carbon-12 is to decay into beryllium-8 nucleus and an alpha particle. The carbon nucleus is initially stationary, and the beryllium-8 nucleus and the alpha particle move as a result of the decay. Compare the momentum of the kinetic energy of the beryllium nucleus to the momentum and the kinetic energy of the alpha particle immediately after the decay. Ensure to support your answer with a calculation. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to be aware that we need to conserve momentum in this particular collision, in this particular production. So therefore we know the carbon nucleus is initially stationary, so the positive momentum of one must equal the negative momentum of the other. So therefore we can say that the momenta are equal in magnitude yet opposite in direction. So at that point we know that the momentum calculation is that the velocity, therefore if the momentum is the same for both, well then the velocity of the alpha particle must be 2 times the velocity of the beryllium. We see that because we know that the mass times velocity of both must equal each other, and we know that that the mass of the beryllium is double that of the alpha particle from the information given 8 and 4. So at that point we know the velocity of the alpha must be double that of the beryllium. We know that kinetic energy is a half mv squared. Now we know that the mass of the beryllium is twice as much as the mass of the alpha, yet the kinetic energy, so the velocity of the other is twice as much as that. However, the velocity is squared, so one goes up by a factor of 2, the other goes up by a factor of 4, so therefore it'll cancel out to be a factor of 2 increase from the kinetic energy of the alpha compared to the kinetic energy of the beryllium, because that velocity is squared. The next question says, one alpha particle with 2.9 MeV of kinetic energy rebounds from a different stationary carbon-12 nucleus. Show that the closest separation between the alpha particle and the carbon-12 nucleus is approximately 6 femtometers. Then the nuclear radii was initially estimated using the technique of closest approach of alpha particles. Electron diffraction experiments give more accurate determination of nuclear radii. Suggest why. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So what you've got to do is you've been given the kinetic energy to be 2.9 MeV. Now we then, because we want to work out values in meters later, need to have this in SI units. The first thing we need to do is convert MeV to joules. We know that the conversion from EV to joules is 1.6 times 10 to the minus 19. So therefore the conversion from MeV to joules is going to be 1.6 times 10 to the minus 13, because we've got 10 to the 6 from the M. So at that point we can get our energy to be 4.64 times 10 to the minus 13 joules. And therefore we now want to work out our separation. Now we know that the work done is that's 4.64 times 10 to the minus 13, and we know for the electrical fields that the work done is going to be equal to Q times by potential, so therefore it's going to be equal to Q1 Q2 over 4 pi epsilon 0 r. We can therefore make r the subject, because we know the charge of the alpha particle, it's going to be 2 times by 1.6 times 10 to the minus 19. We know the charge of the carbon nucleus, because there's 6 protons there, so it's 6 times by 1.6 times 10 to the minus 19. So we can work out our values to be 6 times 10 to the minus 15 meters. Now this next question, you've just got to be aware of how you determine the nuclear radii. So the idea is that a small de Broglie wavelength, or a de Broglie wavelength of comparable size to the nuclear radius, will allow you to determine the radius size easily. However, the closest approach method depends on the kinetic energy of the alpha particle, which will affect how close it can get to the nucleus before it will be repelled. So therefore, the closest approach, you've just got to know this, provides an upper limit to the size of the nuclear radii, because the alpha particle will not physically touch the outer part of the radius. It'll be repelled by its electrical charge repulsion, so therefore it will be an overestimate. Now the next question says, define the binding energy of a nucleus and then calculate the binding energy of a nucleus of thorium-232. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this question you've just got to be aware of the definition of binding energy. So the definition of binding energy is the energy required to separate a nucleus into its individual nucleus. Now the next question, you've got to then use the information given to work out what this binding energy could possibly be. So you know for a fact that you got a proton number of 90 and then a neutron number of 142, because it's 232 minus 90. We can then work out the mass of the protons by multiplying it by the mass of the proton, which is given to you on the equation sheet, and multiplying that value of 142 by the mass of the neutron given to you on the equation sheet. You can then find the difference in mass between those two values and the mass of the thorium nucleus, which is given in the question. You've then got your mass defect, and therefore you can turn this into an energy, and now you've got your mass in kilograms, so therefore you can work out your energy by doing E equals mc squared to get 2.9 times 10 to the minus 10 joules. So this next question says the thorium-232 nuclei absorb neutrons and become uranium-233 nuclei after a series of radioactive decays. Deduce the proton number and the nuclear number of R. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to be aware that when you have absorbing a neutron, well, you're going to increase your neutron number, but not your top number, okay? And you've got to be aware that with the beta decay, you're going to not change the top number, but you're going to increase the value on the bottom by 1. So what you can see here is that if you're going to conserve the numbers for R there on either the middle line or the bottom line, well, therefore the proton number needs to be 91, because from the middle line, 90 equals 91 minus 1, and then again on the middle line we know the value is going to be 233, because 233 equals 233 plus 0. The next question says uranium-233 nuclei undergo neutron-induced fission. One possible fission reaction is shown below. Table 2 shows the binding energy per nucleon for each nucleide. Calculate in joules the energy released in the fission reaction. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So what you've got to do is you've got to work out the binding energy for each of the values by multiplying the binding energy per nucleon by the number of nucleons for each of the values, which is given by the top number for each one. So you work out the binding energy for each one of those values and you get them in MeV. You then got to find the difference between the neutron and the uranium, okay, which is the starting nuclei, and the exon, the SR, and the 3. Remember, there's 3 of them, 3 neutrons, because that's the products afterwards. And then at that point, you find that difference, okay, which is expected to be 182.33 MeV. Then you can convert that into joules by using your conversion factor, which is 1.6 times 10 to the minus 13, as explained before, to get your answer to be 2.9 times 10 to the minus 11 joules. The next question says, when a large number of nuclei of uranium-233 undergo fission, the average energy released per fusion will be different to your answer in the previous question. Explain why. Then the critical mass of uranium-233 is 16 kilograms, so that the radius of a sphere of uranium-233 of critical mass is approximately 6 centimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you've got to be aware that different fissions will produce different types of nuclides, and these different nuclides will have different binding energies per nucleons, which will give a different difference in binding energies, which will give a different energy released. Now in this next question, we've been given our density and we know what the critical mass is, so we know density and mass, so we can work out the volume by doing density is equal to mass over volume. Now therefore we can use the idea that the radius that the object, the nucleus, is a sphere, because it tells us that in the question, so we know that the volume of a sphere is 4/3 pi r cubed. So at that point we can work, we've got V from the equation density equals mass over volume, we know 4/3 because it's a number and pi because it's a number, so we can work out what r is going to be, and we get 5.9 times 10 to the minus 2, which is approximately 6 centimeters. The next question says this ratio of surface area to volume for a 3D dimensional object is sigma, where sigma equals surface area over volume. So determine sigma for the sphere in the previous question, then explain why a cylinder of uranium-233 with a mass of 16 kilograms is unable to sustain a fission chain reaction. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question you've just got to be aware of how you can link the surface area and the volume for a sphere. So we know that the surface area is 4 pi r squared, and we know that the volume is 4/3 pi r squared. So we can cancel out the values of 4, we can cancel out the pi's, we can cancel out 2 of the r's present, so we therefore get that sigma is going to be 3/r, and then at that point we know what the value of r is from the previous question, so we can work it out there to be about 50. Now the next question is explain why it can't sustain a fission chain reaction. It's the idea that we need, on average, for a sustained chain reaction, 1 neutron on average per fission event to then go on to lead to another fission event taking place. Now the idea is if you've got a large surface area, most of those neutrons produced in the fission events will leave the actual object without causing another fission event, because it's less likely to hit another nucleus. So at that point the fewer neutrons will induce less fission, so at that point there'll not be enough neutrons produced to lead to a one-to-one fission event each time, so it cannot maintain that fission process. The next question says, define the activity in the context of radioactive decay. Then a dice roll and experiment models radioactive decay. The standard 6-sided dice are used. One dice represents one radioactive nucleus, and at time t equals 0 there are n0 dice. The dice are rolled and the dice showing 6 dots on the top surface are removed as shown. The number of n of remaining dice is counted. The process of rolling, removing and counting the dice is repeated at intervals of 1 minute. In this experiment, the variation of n with time t can be modeled mathematically with n equals n0 e to the minus lambda t. Explain why lambda is approximately 0.2 minutes to the minus 1. So pause the video now, then unpause the video when you want to go through your answer. Right, the first thing is you've just got to know what the definition of activity is, which is the number of nuclei decaying per unit time per second. It can't be per second, it's per unit time, so it's the number of the nuclei that decay in a particular time. Now how is this value for lambda going to be 0.2 minutes to the minus 1? Well, we know that on average when you roll a dice and there's no loading of the dice, that one dice in 6 will actually roll that value of 6 dots, so therefore the chances getting that is 0.17 is removed each minute for every one dice. So therefore what you can do is you can work it through by doing that. You can say that you work it through to be 0.16, so therefore it's going to be roughly 0.2. Now the next question says estimate the time t at which n equals n0/2, and then say this experiment is done with n0 equals 500. Estimate using the mathematical model for the variation of n with time t, the time t at which n equals 20, then explain why the actual time taken may be significantly different to your estimate in the previous question. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? So you should know that n over 2 is going to be 1 half-life, because that's what the definition of half-life is, the time it takes to drop from n to n over 2. So we can therefore look at our equation sheet and see that half-life is equal to log 2 over lambda. So what we can therefore say is we know that lambda from our previous question is going to be 0.17 or 0.12. So at that point we do log 2 over that value of 0.17. So therefore we can work it out to be 3.8 minutes or 4.2 minutes if you use the actual value that is given precisely, which is 0.17. Then the next one is we sub in our values to n equals n0 e to the minus lambda t. We've then got to rearrange it, and we've got to make t the subject. Again, remember, if you want to take an exponential down to be a common term in your equation, you've got to use natural log. So we would say that natural log n over n0 is equal to natural log e to the minus lambda t. So that natural log and e will cancel through. So we know that natural log n over n0 is going to be equal to minus lambda t. So therefore we can work out what t is after we've done that. We know what n is, okay, which we know to be, so we know what n is and we know what n0 is, because we know n is 20 from the question, n0 is 500, so you can work it all through. Remember that we got our decay constant lambda in terms of minutes, or minutes to the minus 1, so if you keep it in that value, we'll get our answer in time in minutes, so you work it all through and we get 19 minutes. Now, why will this be significantly different? Well, if you think about it, from the question we've told, if you look on here, we've only got about 500 dice. So that's only a really small number of dice, and rolling dice is a completely random event. We've assumed that it's going to be equal probability, but we don't particularly know that, so therefore it's different to decay processes, because rolling of dice is also a discrete event, and the rolling and whilst the decay is happening continuously, so therefore it might be completely different. So that brings an end to our revision session today. If we've been successful in our revision session, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So thank you very much for watching this revision session on Physics Paper 2 for AQA A-level physics. Thank you very much and have a lovely day. Hello and welcome to this revision session for A-Level Physics Paper 2. So in today's revision session, what we're going to be doing is we're going to be looking at how to answer examination questions on AQA A-Level Physics Paper 2. So if we've been successful and we've learned in today's lesson, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? Well, when you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. When you're doing this, make sure to write in full sentences and show your full working out, whilst in the right hand side write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. And after the end of the revision session, write up these notes into a revision sheet for you to use independently. So how can you be revising AQA A-Level Physics? So the first step is to learn the key facts. Use the revision guide, class workbooks, prep notes in the textbook to learn the key ideas of the course, and you might wish to write a mind map or write out notes for yourself. The second step is to retrieve your knowledge and understanding. So use Caboodle, Seneca and knowledge checkers. Use cue cards to quickly test your own knowledge. Then finally, you should be practicing exam style questions. So using exam prep books, homework books, study books, workbooks to answer exam questions and mark your own work, and this could include downloading past papers from the websites. Now these three steps of learning key facts, then testing yourself, then practicing exam style questions are how you should revise AQA A-Level Physics. So let's now have a look at some questions regarding paper 2 for AQA A-Level Physics. So the first topic we'll look at is gravitational fields. So the first question says, the lines in figure 4 show the shape of the gravitational field around two stars, G and H. Compare, with reference to figure 4, the masses of G and H. Then the next question says, X and Y are 2 points in the field. Annotate figure 4 to show the field direction at X and the field direction at Y. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this question? Well, it's important that you know what a gravitational field shows. So you can see that G has the greater mass. How can you see that G has the greater mass? Well, we know that because the field lines coming from G are closer together, and the density of the field lines tells you about the gravitational field strength, which is linked to the mass of the object. The greater the gravitational field strength, the greater the mass of the particles. Now the next question is asking what would you draw for x and y. So it's important to note that what you would do is you draw tangential arrows at x and y that flow towards G and H, because a field line in a gravitational field will always go in the direction of a test mass, and because the gravitational force is always attractive, that means the test masses will always be going towards the particles that are shown, so therefore the field lines will be going towards the objects. The next question says a spherical asteroid P has a mass of 2 × 10 to the 20 kilograms and the gravitational field strength at its surface is 0.40 newtons per kilogram. So use this to calculate the radius of P. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, what you should understand is you should look on your equation sheet and you can see that the gravitational field strength is equal to big G m over r squared. So you've realised you've got the mass of the object, you've got the gravitational field strength, and you need to work out the radius r. Now what you should do is rearrange the equation to make r the subject, so r is equal to the square root of big G m over small g, pop in the numbers and you work your answer through to be 1.8 × 10 to the 5 metres. The next question says, sketch on figure 5 the variation of the gravitational field strength G with the distance r. The distance is measured from the centre of P, and then explain what is represented by the area under the graph between r equals big R and r equals 2r in figure 5. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, what you should understand is as follows, that the gravitational field strength is linked to the distance by the equation G equals big G m over r squared. So because G and m in this instance are constants, we can say G is directly proportional to 1 over r squared. So it's going to follow the inverse square graph. So it should look like so, but what you should also be doing is working out what the values are. So you can see that when the radius is equal to r, well then the value is going to be 0.40. When it's equal to 2r, well again it's G is proportional to 1 over r squared. So therefore it'll go down by a factor of 4 because we've doubled the radius, so there comes 0.2. You can then do the same for 3r to then show that particular relationship, and making sure that you actually work out the individual values. Now again, what is represented by the area under the graph? Well, it's important to know that the area under the graph represents the work done for an object of 1 kilogram or per unit mass to move from r to 2r. So again, it's very important to know what graphs show in AQA A-level physics, and remember you can work it through by saying that the area under a line is going to be the y-axis value times by the x-axis value, so that tells you it's going to be the work done in this instance. And remember, it's for a test mass because that's what definitions come from, and it's going from r to 2r. The next question says asteroid P approaches the 2 stars G and H. Figure 6 shows one position of P close to H. Now the gravitational force on P from G is 6.38 × 10 to the 12 newtons. Now the mass of H is 3 × 10 to the 25 kilograms, and the mass of P is 2 × 10 to the 20 kilograms. The distance HP is 1.5 × 10 to the 11 meters. Calculate the magnitude of the acceleration of P. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? Well, what we know straight away is we're asked to work out magnitude, and we've been given something like the gravitational force, so how can we link it all together? So what we can say is we can say F equals Gmm over r squared to find the force between P and H, because we can tell straight away that there's going to be the gravitational force between P and H, but also P and G. So you can work it through. So you can work it out by saying F equals Gmm over r squared. Remember, big M is the mass of the larger object, small m is the mass of the smaller object, r is the separation between the two centers of mass. So you can work it out to be 1.8 times 10 to the 13 newtons. Now what we can see is we've got a right angled triangle where we have two sides of the right angled triangle, and we need to work out the resultant. So we can use Pythagoras. And again, it's very important that you can recognize when you've got to use trigonometry in different examples in physics. So we can then say F total square is equal to the square root of the gravitational force between P and H squared plus the gravitational force between P and G squared, and then you work it through to be 1.9 times 10 to the 13. Remember, it's important to note that the gravitational force will be a vector, so you've got to consider what the overall vector is going to be on that particular object. We can then use the equation F equals ma to work out the acceleration. There's always a big alarm bell going off when you've been given a force and asked to work out an acceleration that you're going to have to use Newton's second law. So acceleration is force over mass. We can pop the numbers in, so it's 1.9 times 10 to the 13 over 2 times 10 to the 20, so we get 9.4 times 10 to the minus 8 meters per second squared. The next question says, the Global Positioning Satellite GPS uses satellites to support navigation on Earth. One GPS satellite is in a circular orbit at a height h above the surface of the Earth. The Earth has a mass of big M and a radius of r, so that the angular speed of the satellite is given by omega is equal to the square root of gm over r plus h cubed, and then calculate the orbital period of the satellite when h equals 2.02 times 10 to the 7 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, the first thing to note is we're trying to show the angular speed, so how can you work that through? So it's very important that you can relate the gravitational force, okay, which is going to be gmm over r squared, is going to be equal to ma. That's important because it's shown that it is the resultant force in this situation, but it's also equal to the centripetal force, so therefore equals mv squared over r. So at this point we can then work through our value of omega. Now again, you can work through the values. Now straight away you actually probably can think that because we need to work out our value in omega, that maybe it's better if we have our centripetal force in terms of omega. So instead of using mv squared over r, we could maybe use mr omega squared and then work our value through. So we can say gmm over r squared is equal to mr omega squared, and then what you can do is cancel through the small m's because they'll be linked together, make omega the subject, so you say omega equals the square root of gm over r cubed. Now r cubed, it works through to be r plus h cubed because actually the radius that you're going to work out, the small r, is the distance from the center of the object to where the center of mass of the object producing the gravitational field to the center of mass of the object that is in orbit. So in this case it's going to be the radius of the planet, big R, plus the circular orbit height, h. So it works through as so. Now in the next question, you're going to have to use this equation. So we're going to have to use this equation of omega equals the square root of big G m over r plus h cubed by popping in all the numbers from the previous question. Remember, we work in meters in our values to get our speed, our angular speed in radians per second to be 1.45 times 10 to the minus 4. We can then look on our equation sheet and see that the time period is 2 pi over the angular speed. So you're 2 pi over the value to get 4.3 times 10 to the 4 seconds. Always look on the equation sheet to see how we can link the values together. The next question says, figure 3 shows the orbital plane of the satellite inclined at the angle to the equator, and x, y and z are locations on the Earth. X is at the North Pole, y is on a high mountain, and z is on the equator. The satellite is to be launched from one of these locations. State and explain which launch site, X, Y or Z, minimizes the amount of fuel required to send the satellite into orbit. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you can either consider it in terms of speeds or energy. So the answer would be Z, because you've got to think about the idea that at that position the satellite has the largest initial speed or the largest kinetic energy from the Earth's rotation, because you should be understanding that at the equator we've got the highest angular speed. So at that point we can then understand that it'll have the most kinetic energy from the Earth's rotation itself, so it'll need the least amount of energy from the fuel it is given to have enough energy to escape the Earth's gravitational field. The next question says, the satellite has a mass of 1,630 kilograms. Calculate the gravitational potential energy of the satellite when in orbit in the previous question. And then a different satellite is in a higher circular orbit. Explain how the linear speed of this satellite compares with the linear speed of the satellite we worked out previously. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, it's important we understand how we can work out the gravitational potential energy. Now again, because we're looking at orbits, we can't use the equation E equals mg delta H. We've got to use the equation that gravitational potential energy is equal to minus gmm over r. Now we've got big G, it's a constant. We've got the two masses because we've got the satellite mass and we've got the mass of the Earth, so we can pop those into the equation. We then divide it by the separation between the centre of the Earth and the satellite, so we can work it through to be minus 2.44 times 10 to the 10 joules. Now again, remember, gravitational potential energy is always given as a negative value because the gravitational force is attractive, and we set infinity to equal 0 gravitational potential energy. Now the next thing is we can see how the linear speed of the satellite compares with the previous one. Now we've just looked at the idea of how we can work out angular speed, but how can we work out the orbital speed? Well, we can work out the orbital speed by equating the values are the gravitational force equation, F equals g mm over r squared to equal mv squared over r, and then make v the subject. So with that we can work out our orbital speed to be v equals the square root of gm over r. Again, you always should understand how to work out the escape velocity from equating energies and work out the orbital velocity from equating forces. So therefore v is directly proportional to 1 over the square root of r. So by that logic, you can see, in fact, that the higher orbit will have the smaller linear speed from that justification. Let's have a look at some questions on electrical fields. So the first question says, an isolated solid conducting sphere is initially uncharged. Electrons are then transferred to the sphere. State and explain the location of the excess electrons. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you can tell that the electrons are going to be located on the outer surface of the conducting sphere, and that the electrons will be equally spaced on this sphere. Why is that? Because the electrons will mutually repel each other because they're all negatively charged, so they'll want to spread away from each other as much as possible due to that electrostatic repulsion, so they'll be equally spaced out on the surface. The next question says, figure 3 shows how the electrical potential V varies with distance r from the centre of the sphere. The radius of the sphere is 0.10 meters. So the magnitude of the electrical field strength E is related to V by the equation E equals delta V over delta R. So determine, using this relationship, the magnitude of the electrical field strength at a distance 0.30 meters from the centre of the sphere, and state an appropriate SI unit for your answer. Then the sphere acts as a capacitor because it stores charge at an electrical potential. Show that the capacitance of the sphere is approximately 1 times 10 to the minus 11 farads. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, it's important to note that you've got to work out the gradient by saying, well, obviously E is linked to V by E is delta V over delta R, so from the graph that's going to be the gradient. Now it's going to be the value at 0.30 meters, so because it's curving you will have to draw a line as a tangent which only hits the curve at 0.30 meters. You've then got to explicitly show how you work out the gradient of the tangent by literally drawing in your gradient triangle, and it's got to cover at least 50% of the line drawn from your tangent. You then work out the value through and you get an answer of approximately 2 times 10 to the 6. Now what's the units going to be? Well, if you think logically about this, it's going to be V, okay, over M, because we're doing the potential over the distance, so it's going to be 1 unit over the other unit, which is volts per meter, or you could also remember the units for electrical field strength from the definition. It's the force per unit charge, so it's newtons per coulomb. Now in this next question, what do you do? Well, you can work out what the value of V is. The value of V, it can work out your value of charge by saying V equals Q over 4 pi epsilon 0 R. So you can then look on your graph and work out what the charge would be by saying Q equals V times by 4 pi epsilon 0 R, and then you can work out that value. Now you've also got the electrical field strength at 0.30 meters, so you've got your electrical field strength there. Now because it's a capacitor, we can say that the capacitance is equal to the charge over the potential difference. So therefore we've just worked out the charge in the previous time to be 2 times 10 to the minus 5 divided by your potential difference, which you can then work out to be 1.8 times 10 to the 6. So we get our capacitance of 1.1 times 10 to the minus 11 farads. Or you could also work the other way and say that, well, C equals Q over V. We can work out V by doing V equals Q over 4 pi epsilon 0 R. So therefore C is going to equal 4 pi epsilon 0 R times by V, and work it through to be again 1.1 times 10 to the minus 11 farads. The next question says, electrons leak away from the sphere with time and the amount of energy stored by the sphere decreases. At one instance, the magnitude of the electrical potential of the sphere has fallen to 1 times 10 to the 6 volts. Calculate for this instance the change in the energy stored by the sphere. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? So, you'll note that E is equal to a half CV squared. Now, how do you know that? Well, that's given to you on the equation sheet. How do you know to use that value? Well, you think you've just worked out C, you've got V in the question, so it allows you to easily work out your value. So you can work out what the energy stored is going to be at 1 times 10 to the 6 volts. So then what we can do is then work out the energy stored when it's fully charged. Again, you can see on the graph when it's going to be fully charged. So at that point, you can work out that value there. You find the difference between the two, so it's 18 minus 5.5 to get 12.5 joules. Let's now have a look at some questions regarding capacitance. So the first question says, a capacitance of capacitance 63 picofarads is made from 2 parallel metal plates separated by an air gap. The capacitor is charged so that it stores a charge of 7.6 times 10 to the minus 10 coulombs. It is then isolated. A sheet of mica of dielectric constant 6 is inserted between the plates so that it completely fills the space between them. The mica does not discharge the capacitor and does not change the separation of the plates. Firstly, explain what is meant by a dielectric constant of 6. Secondly, mica is made up of polar molecules. As the mica is inserted, the capacitance of the capacitor changes. Explain how the polar molecules cause this change in capacitance. So pause the video now, then unpause the video when you want to go through your answer. Right, well this first question is asking you to fundamentally define what we mean by dielectric constant. So the definition of dielectric constant is it's the permittivity, which is the ability to make an electrical field, of the medium divided by the permittivity of free space. So what we are saying by that is that the permittivity of the medium, the actual dielectric, is 6 times the permittivity of free space. It can find it easy to generate electrical fields by 6 times the magnitude compared to what free space can. The next question is asked us to understand how polar molecules can change the capacitance. So it's important to note that polar molecules align anti-parallel with the electrical field. So that means the positive side of the polar molecules aligned with the negative plate and vice versa. So because they're all lined up, that will produce a very coherent electrical field from the polar molecules. But because they are aligned in the opposite direction, anti-parallel to the actual uniform electrical field, it will produce an electrical field in the opposite direction, so it counters the electrical field between the uniform plates and reduces the field between the plates. So as a result, the potential difference has now been reduced, but the charge remains the same. So because C equals Q over V, well that tells us that the capacitance has increased, that the capacitor finds it easier to store more charge between the plates. The next question says, a capacitance of capacitance 63 picofarads is then made between the 2 parallel plates separated by the air gap. Now calculate the difference between the initial energy stored by the capacitor and the energy stored when the mica has been fully inserted. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this one? Well, we know in this question that the charges remain the same. So we know Q is the same, but the new capacitance is 6 times out of the previous one because the dielectric constant is now times by 6. So when we look at the equation, for example, you can look at your dielectric constant equation by saying, C equals A over epsilon 0 epsilon r d squared. So what you can say by that is the new capacitance is going to be 6 times the size of the previous ones. So you can work it through by saying if Q remains the same but capacitance goes up by a factor of 6, well, then our energy difference is going to be 3.8 times 10 to the minus 9 joules. The next question says, Figure 1 shows the structure of a variable capacitor used for measuring angular movement. The capacitor consists of 2 semicircular metal plates. These plates are parallel and are separated by an air gap. To vary the capacitance, one of the plates is rotated through an angle theta using a spindle. The other plate remains fixed, so sketch a graph on Figure 2 to show how the capacitance C varies with theta as the spindle is turned through 360 degrees. When theta is 0, the plates completely overlap. So pause the video now, unpause the video when you want to go through your answer. Right, in this question it's important to note that you will get your biggest capacitance when the plates are fully overlapping, because you'll then get the biggest potential difference between the two plates. So the positive and negative will form the strongest uniform field when they're completely overlapping. So you can see that when they're completely overlapping that they're going to have the biggest value of C. Now when they're not in alignment, when they're not overlapping, so to 180 degrees, well therefore you're going to get a capacitance of 0 and then it bounces back up as it moves to 360. Now it's important to note that it's going to be a linear decrease and a linear increase because you've got a constant rate of rotation, and you can think about how they will overlap, and that will constantly change how much overlaps. The next question says, in one situation the variable capacitor is too large for the available space. The same maximum capacitance is required using plates that have half the diameter of the original capacitor. Explain with numerical detail 2 ways in which this can be achieved. So pause the video now, then unpause the video when you want to go through your answer. Right, how do you answer this particular question? So you've got to think how we can have the same maximum capacitance required when using half the diameter of the original capacitor. So you look at your equation for your parallel plate capacitor of C equals A over epsilon 0 epsilon r d squared. So you can see that you can either insert a dielectric between the plates, and it's important to note that you would increase it by a factor of 4. So as a result you can then counteract the fact that you got half the diameter, because if you remember in the equation we don't have diameter but we've got area. So diameter links to area by a factor of a square. So when the diameter is halved, okay, well that's going to tell you is the area is going to go down by a factor of 4. So therefore we've got to put a dielectric of 4 in to counteract that difference. But the other issue you can do is you can change that value of D. So you can reduce the air gap to a quarter of the size, again because again it's being divided by that. So as a result what it'll do is you'll have a quarter of the area and a quarter of the diameter, so the separation, sorry. So as a result the two will cancel through to get the same value. Now note it says explain with numerical detail, so with that we actually had to say how much the value would be changed. Let's now have a look at some questions regarding thermal physics. So the first question says, Figure 1 shows an electrical steam iron. Water from a reservoir drips into the electrically heated metal plate. The water boils and steam escapes through the holes in the metal plate. The electrical power of the heater inside the iron is 2.1 kilowatts. Assume all the energy from the heat is transferred to the metal plate. The metal plate has a mass of 1.2 kilograms and is initially the temperature 20 degrees Celsius, and the heater is switched on. After a time t, the metal plate reaches its working temperature of 125 degrees Celsius. Calculate your value of T. So pause the video now, then unpause the video when you want to go through your answer. Right, the first thing you notice is in the question you're given the power. Now you should also remember that with specific heat capacity that the equation where that incorporates in is that energy is equal to MC delta T. Now we also know that E is equal to PT, so what we can do is we can work out what the energy is, or in this case we says Q, by doing the power, which is 2.1 times 10 to the 3, because we don't work in kilowatts, we work in watts, multiplied by the time in seconds. Now again, if you read the question here, it says that it has been on there, so it's been on for time t, so we can say that it's going to be equal to 2.1 times 10 to the 3 times by t. We can then say, well, that substitutes into Q, and then equals the mass, which is 1.2, times by the change in temperature, which is 125 minus 120, times by the heat capacity. We then rearrange it and use that to work out T, which is 27 seconds. The next question says the metal plate is maintained at its working temperature. Water 20 degrees drips continuously onto the metal plate. Steam at 100 degrees Celsius emerges continuously from the iron. The maker claims that the iron can generate steam at a rate of 60 grams per meter. Determine whether this claim is true. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, what you've got to understand is that the power supplied in time t will raise the temperature of the mass of the water and convert it into steam. So what you should be doing is you should then be using an equation to work out different values. So what we can say is that the energy supplied, which is the power times by time, is equal to mc delta t plus ml. And as a result, we can use that to work out what P is, because in the question, we've got the heat capacity, we've got the specific latent heat, okay, and then what you can then do is we've got the mass as well, so as a result we can work out what the power is, and then as a result we can link that back into how we can generate steam at 60 grams per minute by working it out as such. So you can work that then through to work out your value. So you can work out your power to be 2.6 times 10 to the 3 watts. We can then work out how many grams that would then convert per minute, and then you can see if the value is correct. Now again, it's really important to note in these questions you actually answer the question asked, so you've got to evaluate and say whether the claim is false or whether the claim is true. So the idea is it is probably false because it's not going to be supported by the values, because the calculated quantity you're going to get is going to be not the same as the value that you need. The next question says, in the kinetic theory model, it's assumed that there are many identical particles moving at random. So state two other assumptions made in deriving the equations PV equals a third N mc RMS squared. Then explain why molecules of a gas exert a force on the walls of a container. Refer to Newton's laws of motion in your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, you've just got to know the assumptions of the molecular kinetic theory. So they are the volume of the molecules or the volume of the particles is negligible compared to the volume of the container or the volume of the gas. Okay, but remember, you can't just say the volume of the gas, you've got to say the volume of the container which the gas is in. And then you can also say that the collision time is negligible, or it's very small compared to the time between the collisions when the particles are in motion. The collisions between all the particles and the containers are elastic, which means that kinetic energy and momentum is conserved in these collisions, and that finally there are no attractive forces between the molecules or the particles when they exist in the gas state. Now you can also got to be able to explain how a gas can exert a force on the walls of a container, which links back into paper 1 and the idea of mechanics. So it's the idea that when a particle collides with the side of a container, there will be a change in velocity, so therefore there'll be a change in momentum. Why is that? Because we're changing direction, and velocity is a change in speed or a change in direction. Or if you want to think about it mathematically, it goes from a positive momentum to a negative momentum, so therefore there's a change in the momentum of the molecules. So what we know from Newton's second law is that Newton's second law is the idea of that the resultant force is linked to the rate of change of momentum. So because there's a rate of change of momentum, there will be a force produced onto the wall. Now again, with Newton's third law, the force on the wall and then the force on the molecule must be equal yet act in opposite directions, because they are a third law pair. So you've got the same magnitude of force, the same type of force, but they act in opposite directions on different objects. So as a result, you'll get a force on the particle. The next question says, a sealed flask of volume 0.35 meters cubed contains an ideal gas at a pressure of 220 kilopascals. The mean kinetic energy of the gas molecules is 6.7 times 10 to the minus 27 joules. So calculate the amount of gas in the container. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do we answer this particular question? So First question is how can we link the different equations together? So we should hopefully know that the kinetic energy of one gas particle, we can look at our equation sheet and we see that it's 3/2 kT. So straight away we've got the mean kinetic energy of one particle. We know what K is, so we can use that to work out the temperature. So we pop that in and we make T the subject and we get T out to be 324 Kelvin. Remember, in this equation the temperature is given in absolute, so it's in Kelvin. So then what we can do is because the question's asked us to work out the amount of gas, is we've got to work out how many particles are present. So as a result we can then use one of the equations to say like EK is equal to a half MC RMS squared, to then we can work out what N is going to be, or we use PV equals a third NMC RMS squared to work out our value of N. Or what we could also do is use now our equation of PV equals nRT to work out small n, the number of moles. So we could say number of moles is PV over RT. We've just worked out what T is. We know R, it's the molar gas constant. It's given in the equation sheet. We've got a value for pressure, 220 times 10 to the 3, because we don't work in kilopascals, and we've got a volume of 0.35. So that allows us to work out how many moles that we have, and then we can work out our answer to say the answer is going to be 29 moles. Now the next question says, figure 2 shows a variation of pressure with volume for a fixed mass of an ideal gas at a constant temperature of T. Draw on figure 2 the graph for the same gas at a temperature 2T. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? So you've got to have an understanding of what the actual graph is showing, so a PV graph. So you would draw a graph with the same concave shape, because it's going to have the same trend, because it's still pressure and it's still going to be volume, it's just a different temperature. But now it's going to pass at points, okay, where it's going to be higher. So you can see here it's passing through the coordinates of 2 and 8, 4 and 4 and 8 and 2, because you can see that with the increased temperature there, well, it's going to increase both the pressure and the volume of the gas. So you've got to think to yourself, how would it affect it? It would just cause both of them to double. So whilst the PV value is going to be constant, then as a result, okay, it's just going to be increased values, because when you've increased your temperature, well, therefore you've got a higher pressure because the particles are moving faster, and also you're going to increase volume because the particles are moving further. So it's the same trend but just higher. Let's now have a look at the magnetic fields topic. So this question says figure 7 shows a transformer. Explain the functions of the core and of the secondary coil in the transformer. So pause the video now, then unpause the video when you want to go through your answer. Right, so what's the core and what's the secondary coil? You've just got to know this. The core is what provides a great flux linkage, or increases the flux linkage from the primary coil to the secondary coil. So it's directing, it is concentrating, it is funneling, it is focusing the linkage from the primary coil towards the secondary coil. Now what is the point of the secondary coil? That is where we get a change in magnetic flux linkage passing through it, or there's a change in magnetic flux linkage, the field lines going through a conductor. So as a result, because there's a change in flux linkage going through the secondary coil, it tells us that we're producing an EMF, or inducing an EMF. That's Faraday's law. So therefore we can work out what the actual value of the EMF is going to be by looking at the ratio of the number of turns of the secondary and the number of turns of the primary. You can see that's a big deal, and the question goes to make a big deal about having a different number of coils on this particular transformer. Now the next question says figure 8 shows the cross section through a transformer core. The thin iron sheets are separated by arterial M. Explain how the efficiency of the transformer is increased by constructing the core in this way. And then figure 9 shows a schematic diagram of a power transmission system. Voltages between 33 kilovolts and 400 kilovolts are used for long distance transmission. Suggest why engineers have chosen 132 kilovolts for this system. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you should understand is when you see an M in this particular transformer, well, M is going to be a insulator. Now when we cover a material in insulation, that is called lamination. So these laminations or laminates are made from an insulator or high resistivity material. Now why do we have this? Well, this reduces the impact of eddy currents in the transformer, because they've got such a high resistance you won't get a high current forming. Now because if you look at the question, it's 3 marks, we need to think about other features of this which will increase the efficiency of the transformer? Well, you've got to think of the idea that because we're using thin sheets or laminates of iron, we'll get smaller EMFs induced in the core, so we won't get that high enough eddy current. And also we'll note that the thin sheets of iron are used, the resistance is going to be higher, so as a result, once again, our eddy currents will be lower. Now, the other thing to note is it makes a big deal that we're using iron in the core. Now, the iron is important because the iron can magnetize and demagnetize very easily. It's a soft magnet, so therefore what you're going to have is you're going to have it's not going to have much energy loss due to hysteresis, so that's another reason. Now, the next question, why would you use 132 kilovolts for this system? Well, you've got to look at the different values and compare, because if the voltage is lower than 33 kilovolts, then the power transmitted is at a high current. Think about why this is, because V and I are inversely proportional in a transformer. When V goes up, I goes down, and vice versa. Now, we know the equation for power loss in a cable is P equals I squared R. So if we have an increased value of I, it will have an increased power loss in the cable. So as a result, we don't want it any lower because we'll have the current is too high. But then you've got to also think, why do we have a really high volts? Why not higher than 132 kilovolts? Well, it's because if the voltage is too high, this will create major difficulties with keeping the circuit insulated and isolated, because there'll be a massive potential difference with the surroundings, so therefore it could cause an electrical discharge. So you can't have that big of a potential difference. Remember, electrical shocks are caused by a large potential difference between the objects. The next question says the industrial consumers use 72 megawatts of power. Transformers 1 and 2 each have an efficiency of 98%, and the transmission line has an efficiency of 94%. Calculate the current in the 25 kilovolt line from the power station. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to remember that efficiency is going to be the useful power out divided by the total power in. Now, we can also use that the current is P over V to work out particular values. So what you've got to do is you've got to work out at each point in your national grid system what the power is going to be after you've considered the efficiency of that, and then what you do is at the end you work out the current by doing I equals P over V, from the P that you've just got left and the V that you've got right at the end, because you know it's going to be 25 times 10 to the 3. So the first point is at 132 kilovolts. We know that it's got an efficiency of 98%, so we do 132 kilovolts times by equals 72 over 0.98, so therefore we're going to have 73.5 megawatts at that point. And then you can see that the next section, that's going to have an efficiency of 94%, so we multiply that by 0.94 and we get that's 94%, so therefore the transmission at the start is going to be 78.2 mega EV. And then what you can do is then work it all through, and then you can work out your values, pop them all in, work it out the end by doing I equals P over V to work out our answer to be 32,000 or 3,190. Let's now have a look at the nuclear physics topic. So the first question says fission and fusion are two processes that can result in the transfer of the binding energy from the nuclei. State what is meant by the binding energy of a nucleus, then calculate in MeV the binding energy of a nucleus of iron 5626 Fe. So pause the video now, then unpause the video when you want to go through your answer. So the first question is all about definitions, and you've just got to learn it. That the binding energy is the work done required to separate the nucleus into its individual nucleons, its individual protons and neutrons. So it's how much energy is needed to separate out your nucleus completely. Now in the next question, how do you work out the binding energy? So what you've got to do is you look at the values here and you work out the mass defect. Now you work out the mass defect by working out the masses of the individual nucleons, and then we subtract the mass of the nucleus from that, because that's the difference. So we see that there are 26 protons in iron, so we do 26 times by the mass of the proton. That is given to you on the equation sheet. You can see here that 56 minus 26 is 30, so we've got 30 neutrons. So we know that we do 30 times by the mass of the neutrons in kilograms, which is given on the equation sheet. You add them together to get the total mass of the individual nucleons. You then subtract that from the from the mass of the nucleus, and then as a result you then got your mass in kilograms. You can then convert that into joules by doing our equation E equals mc squared. Now that gives us our value in joules, so E equals the mass deficit times by the speed of light squared. We can then convert that into MeV, because the conversion between joules to MeV is times by 1.6 times 10 to the minus 13 joules. So we get our answer out there to be 490 approximately. Now the next question says, figure 10 shows how a graph of average bind energy per nucleon against nucleon number for common nuclides. So the nuclide labelled X in figure 10 undergoes fission. Annotate figure 10 to show one possible pair of nuclides resulting from the fission of X. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So you've got to think that F1 and F2 have to be to the right of the peak, and they're marked on there in the x-axis. Now again, they've got to be in the correct region, so they're symmetrical to about half the nucleon number. So what you've got to understand is that the two values have to approximately add up to equal that value of about 240. Now again, you've got to remember that it won't exactly add up to what the value was for the original nucleus, because you'll lose a couple of nucleons to become free neutrons to then carry on the fission process. So you'll see here they've got to be roughly symmetrical, two smaller values, they add up together to then give a couple of values smaller than the actual nucleus that you started with. The next question says, figure 11 shows a graph of N against Z for stable nuclides. Deduce the likely mode of decay of F1 and F2 and refer to figure 11 in your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So what you've got to do is you look at what the values are for the fission fragments given in your first question. Now you'll notice that in this NZ graph that all the fission fragments will want to move towards the stability belt. Now the issue with both the fragments that you'll produce is they'll have a high ratio of neutrons compared to protons, N to Z. So that tells us that we've got too many neutrons compared to protons. So therefore we want to get down to the stability curve, we want to move closer to the stability belt. So as a result we've got too many neutrons, so we're going to turn a neutron into a proton, so therefore it's going to have to be the beta minus decay, because that in that process you're turning a neutron into a proton, so as a result it will move closer towards that stability belt. So that brings an end to our revision session in today's lesson. So if we've been successful and we've learned in today's lesson, we'll be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for AQA A-level physics. So thank you very much for watching this particular revision session for paper 2 in AQA A-level physics. Thank you very much for watching and have a lovely day. Hello and welcome to this revision session for paper 2 for AQA A-level physics, which links it into the topic suggested for the advanced examination information for the 2022 examination. So what we're going to be doing in today's revision session is looking at how to answer examination questions on A-level physics paper 2. So if we've been successful and we've learned in today's lesson, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So how do you prepare for this revision session? So when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this section write out your working out and your answers to the questions in the revision session. When doing this, make sure you write in full sentences to show the full working out, whilst in the right hand side in this section write down any piece of information which you find useful or any hints and tips on answering questions from this revision session, and at the end of the revision session write up these notes into a revision sheet for you to use independently. So what are your tips to revise in AQA A-level physics? So first step is to learn the key facts. So use revision guides, class workbooks, student prep notes, textbooks to learn the key ideas of the course, and you may wish to make mind maps or write out notes yourself to learn the knowledge. The second step is to use Caboodle, Seneca, student knowledge checkers to quickly test your own knowledge, and you may wish to retrieve your understanding from using your own cue cards. And the third third step is practice. So practice examination questions by using exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work. And you may wish to do this practice by downloading your own examination past papers to do this. So what should you be doing? Learn the key facts, test yourself, practice exam style questions. So let's have a look at the first topic of thermal physics. So it says figure 1 shows the variation of pressure P with volume V for a fixed mass of gas as is compressed from volume V1 to a volume of V2. There is no transfer of heat energy between the gas and its surroundings during this compression. So estimate the work done on the gas during the compression from V1 to V2. So pause the video now, then unpause the video when you want to go through your answer. Well, it's very important that when you get a PV graph in your exam, to calculate the work done on the gas or away from the gas, it's going to be the area under the graph. So what you should be doing is working out the energy per small square, which is going to be 0.2 joules, by looking at the scales of P and V and multiplying them together. And then you can work out the total number of squares by counting them or working it through with a shape under the graph, and therefore you get an answer between 35 joules and 38.2 joules. The next question says that the density of the gas is 0.179 kilograms per meters cubed when the volume is V1. Calculate the number of moles of gas present, where the mass of 1 mole of the gas is 4 times 10 to the minus 3 kilograms. So pause the video now, then unpause the video when you want to go through your answer. Well, for this type of question, we've got to remember that the mass of the gas is equal to density times by volume. Now, you know that's because density is mass over volume. Now, you really know this is where we're going in the question because we're given density in the actual blurb of the question, and mass as well. So we can work out what the mass of the gas is by saying density times by volume, and you can read the volume off the graph. So you can read the volume of the gas off the graph at V1, so we can work it through, and we can work out the mass is therefore going to be 2 times 10 to the minus 4 multiplied by 0.179. What we can then do is say that the number of moles is going to be equal to the total mass of the gas divided by the mass of 1 mole. Therefore we get 8.95 times 10 to the minus 3 moles. The next question says, calculate the increase in temperature of the gas as a result of being compressed from V1 to V2. Then explain in terms of movement of particles why the pressure of the gas increases when it's compressed from V1 to V2. So pause the video now, then unpause the video when you want to go through your answers. Right, so how would you work it through? Well, we're trying to work out temperature and we're being given P and V. So the obvious place to go is say PV is equal to nRT, an equation given to you in your equation book for your exam. You can then work out your temperature by taking any value off the graph really, but I would say either V1 or V2. So you can take either temperature by working it through and taking the values of P and V on the graph. And then we also know the value of the number of moles from the previous question. So what we can therefore do is work out what the value of T is going to be by working out what the change is going to be 24.2. My apologies. That would be working it out, the increase to equal 328 by working it through for the values worked out from that particular equation. Now the next question is pretty much asking you, why does an increase in temperature cause an increase in pressure? Well, what's going to happen is if we increase the temperature, the internal energy of the gas is going to increase. So this gives our gas particles more kinetic energy. Now the pressure will increase because you've got a greater change of momentum of the gas atoms when they collide with the walls of the cylinder. It's always important to link the pressure to the rate of change of momentum of the gas particles as they collide with the container that they're in. Now, why would you have a greater change in momentum of an increased temperature, which leads to an increased kinetic energy of the gas particles? Well, there'll be firstly a greater frequency of collisions of the gas particles with the side of the cylinder, and also the gas particles themselves will have a greater momentum because they've got a higher velocity, so therefore the change in momentum for each collision is also going to be greater. Let's now have a look at some questions on radioactivity. So the first question says, a stationary uranium-235 nucleus decays to a thorium-231 nucleus by emitting an alpha particle. 98% of the total energy released in the decay is transferred to the emitted alpha particle as kinetic energy. Explain in terms of mass of the nuclei why the total binding energy of the nuclei must increase as a result of this decay. So what you should do is pause the video now and then unpause the video when you want to go through your answer. Right, so how would you answer this type of question? Well, it's important to note that in any nuclear decay, the mass of the product nuclei is going to be less than the mass of the original, the mass of the uranium nucleus. Now, we call the increase in the mass here is the mass defect. So the idea of your binding energy then links by doing E equals delta mc squared, where m is the mass defect. Okay, so therefore you can say that the binding energy is the energy equivalent of the mass defect or the mass deficit. Now, the next question says, a stationary uranium-235 nucleus decays to a thorium-231 nucleus by emitting this alpha particle. So table 2 shows the binding energy per nucleon of the nuclei involved in the decay. Calculate the speed of the alpha particle just after it is emitted, where you're given the mass of the alpha particle in the question. So pause the video now, then unpause the video when you want to go through your answer. Well, how do you answer this particular question? Well, it's important that you can work out the energy released in this particular process. So what we know is we start off with uranium, and we're producing thorium, and we're producing helium in this particular question, because we're producing the alpha particle, which is helium. So what we would say is the energy released is equal to the binding energy of the thorium plus the binding energy of the helium minus the binding energy of the uranium. Now, it's important to note that when you're doing this, the table gives you the binding energy per nucleon. So you've got to multiply all those values in the table by the nucleon number of the particular element. So for 235 for uranium, 231 for thorium, and 4 for helium. What you would then do is you would then work out your energy released in joules to be 0.59 times 10 to the minus 12 joules, because remember the values of picojoules that they'll give you. You can then multiply that value by 0.98. Why 0.98? Well, because 98% of the total energy is then transferred to the kinetic energy of the alpha particle, which is what we're trying to work out. So therefore, once you've worked out our energy value, we can then say E equals a half mv squared, the kinetic energy equation. We know the mass of the alpha particle because it's given in the question. We've just worked out the energy of the alpha particle from our sum just previous, so we can work out V to be 1.3 times 10 to the 7 meters per second. The next question says, a plasma containing nuclei of 2 isotopes of hydrogen, 2H and 3H, is considered to be a possible fuel for fusion reactors in the future. The plasma must be heated to a high temperature to provide the nuclei with the minimum kinetic energy to enable the fusion reaction to occur. Explain why the nuclei in the plasma require a minimum kinetic energy for this fusion reaction to occur. So pause the video now, then unpause the video when you want to go through your answer. Well, this question is pretty much asking you to explain the nuclear fusion process. So the idea is that you've got 2 positively charged nuclei. So the 2 nuclei are going to want to repel each other. So when you need a high kinetic energy, because that will transfer to electrostatic energy due to the repulsive nature of the 2 positively charged nuclei. Now we need to have a high enough kinetic energy so they can get close enough so that kinetic energy will transfer into electrical potential energy, so that the nuclei are close enough so that the strong force can bind the 2 nuclei together. Remember, the strong interaction is the binding force in our fusion process, and the 2 nuclei need to be close enough for the strong interaction to be within the range for it to take hold. The next question says, the radius of a 2H nucleus is 1.51 times 10 to the minus 15 meters. So show that the distance between the 2H nucleus and the center of the 3H nucleus is about 3.2 times 10 to the minus 15 meters when they're just in contact. So pause the video now, then unpause the video when you want to go through your answer. Well, it's important to note that in these types of questions we need to look at the idea of how do you work out nuclear radius. So we know our nuclear radius R is equal to R0 a to the power of a third. Now we know R0 is 1.12 times 10 to the minus 15. So what we can therefore do is we can therefore use R equals R0 times by a to the power of a third for the radius of helium by hydrogen, 3 hydrogen, so we would just go, it would be 1.12 times 10 to the minus 15 times by 3 to the power of a third, so you work it out to be 1.73 times 10 to the minus 15. You've already got the radius of the 2H nucleus, which is 1.51 times 10 to the minus 15, so you add the two values together and you get an answer of approximately 3.24 times 10 to the minus 15 meters. The next question says, assume that the 2H and the 3H nuclei fuse when they are just in contact. Calculate the minimum total kinetic energy that would allow a 2H nucleus and a 3H nucleus to fuse. So pause the video now, then unpause the video when you want to go through your answer. Well, it's important to note in this situation our kinetic energy is being turned into repulsive electrical potential energy due to the positive charges of both the nuclei. So we can equate the two. So we can say that kinetic energy is equal to Q1 Q2 over 4 pi epsilon 0 R, the equation for electrical potential energy. So we can then substitute our values in. So we've got the charge of one, because remember it's going to have one proton. The charge of the other one, again, one proton. We know the separation R because we've just worked it out in the previous question, and we know 4 pi epsilon 0. So therefore we can work out what the kinetic energy is going to be, and therefore we know 7.1 times 10 to the minus 14 joules. The next question says the equation for this fusion reaction is shown here. The table 1 shows the mass of each particle involved. Calculate in joules the energy released when this fusion reaction takes place. So pause the video now, then unpause the video when you want to go through your answer. So in this type of question, it's important to work out the difference in mass in this particular process. So what you do is you do the mass of the helium and the mass of the neutron minus the mass of the deuterium and the mass of the tritium, 2H and 3H. What we can then do is find our mass difference, and that's our value in U. Now we can convert from U into an energy unit, MeV, by multiplying that value by 931.5. That gives our answer in MeV. Then we can convert it into joules by dividing by 1.6 times 10 to the minus 13, because that's our conversion factor from MeV into joules. So we get our answer to be 2.7 times 10 to the minus 12 joules. The other way you could have done it is worked out your mass in U by the same process, then multiply by 1.661 times 10 to the minus 27 to get your answer in kilograms. Once again, that conversion factor is given to you in your equation book. We can then work out our energy release with our mass in kilograms by doing E equals mc squared. The next question says, an alpha particle with an initial kinetic energy of 8 MeV approaches the center of a nucleus of gold 197. Calculate the distance of closest approach between the alpha particle and the nucleus. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this question? Well, again, it's the idea of two positively charged objects coming close to each other. So we can say our kinetic energy is equal to our electrical potential energy. So we say EK is equal to Q1 Q2 over 4 pi epsilon 0 R. Now we want to work out R, so we make R the subject. But what's kinetic energy going to be? It's going to be 8 times by 1.6 times 10 to the minus 13, because we're converting it into joules. We know the charge of the alpha particle to be 2 times by 1.6 times 10 to the minus 19, because it's an alpha particle, so it's got 2 protons. We know that it's got 79 protons in gold from the information given in the question, so it's 79 times by 1.6 times 10 to the minus 19. You can work it all through to be 2.84 times 10 to the minus 14 meters. The next question says, discuss why electron diffraction gives a more accurate value of a nuclear radius than the using the distance of closest approach of alpha particles. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to be able to explain the difference between electron diffraction and the distance of closest approach. Now, the important thing to note is that the most important idea is that the distance of closest approach depends on the alpha particle energy, because it's turning kinetic energy into electrical potential energy. So your value for your separation, R, which you just calculated in the previous question, is dependent on the actual kinetic energy of the alpha particle. Now, the distance of closest approach is dependent on the fact that the alpha particle does not collide with the nucleus. Rather, it gets close enough to then be repelled by the positive-positive interaction. So the closest approach is not the nuclear radius, it's actually the nuclear radius plus another distance, okay, because the alpha particle will not touch the nucleus itself. Now, for our electron diffraction, it's a more accurate value because the de Broglie wavelength of high energy electrons is of the order of the nuclear radius, so it will have diffraction because the biggest diffraction occurs when the de Broglie wavelength is equal to the size of the gap it's going through, which is in this case the nuclear radius, so you'll get large diffraction angles, so it's very easy to measure. Now you'll also note as well that because alpha particles have the same mass on order of magnitude as the nucleus itself, you'll actually get our values affected by a momentum transfer or a nuclear recoil because of how similar in size they are. The next question says, describe with reference to their energy the role of neutrons in a thermal nuclear reactor. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So in this case, neutrons are released in fission. So the fission process will release some neutrons to be free. So these fission neutrons, if you want them to then fission further nuclei, have to be slowed down. So they've got to have their kinetic energy reduced. So this is achieved, this slowing down, it so has a smaller kinetic energy value, is achieved by collisions with the moderator atoms, so therefore that these neutrons are moving slow enough to be absorbed by uranium nuclei to sustain the chain reaction. The next question says, describe the function of control rods in a thermal nuclear reactor, and your answer should include one example of a suitable material for a control rod and its properties. So pause the video now, then unpause the video when you want to go through your answer. Right, so a suitable material for a control rod would either be boron or silver or cadmium, indium, hafnium. They're all examples. I mean, the most common example is boron. Now, what happens in a control rod is a control rod will control, as the name suggests, the rate of fission in your reactor. So what the control rod can do is it can maintain the rate of fission that you want in your reactor. So the control rod does this by absorbing neutrons, because if it absorbs neutrons, it prevents these neutrons from being absorbed by other uranium nuclei and causing further fission. So you've got to know that if you raise your control rods, less neutrons are absorbed, so the fission rate will go up because more neutrons will encounter the uranium nuclei. But if you lower your control rods into your reactor, well then more neutrons are going to be absorbed, so less neutrons will be absorbed by uranium nuclei, so there'll be less fission. If you wanted to shut down your fission reaction as soon as possible, you will completely lower your control rods down. Let's now have a look at some questions on magnetic fields. So this question says, a rectangular coil shown in figure 2 rotates at a constant frequency of 40 Hz about an axis that is perpendicular to a uniform magnetic field of flux density 0.15 Teslas. The coil has a length of 6 centimeters and a width of 4 centimeters and has 25 turns. Calculate the peak in EMF induced in the coil. Calculate the root mean square value of the EMF induced in the coil. So pause the video now, then unpause the video when you want to go through your answers. Right, it's important that if you look in your equation book for AQA A-level physics, you'll notice there's an equation for peak EMF is equal to BAN omega. Now we know omega from our circular motion topic is 2 pi f. Now you've been given F, you know B, you know A by calculation. Now again, remember they're given you in centimeters and you work it out in meters. And we've got our value of N, we know how many turns there are, okay, because it tells you it's 25. So you put all these numbers in and you work it out to be 2.26 volts. The next question says calculate the root mean square value of the EMF induced in the coil. So what you can then do is you can therefore say the root mean square EMF is going to be the value divided by square root 2. So you do 2.26 divided by square root 2, which is 1.60 volts. The next question says, for the same idea, a 6.8 ohm resistor is connected across the output of the coil. Assume the coil has zero resistance. Calculate the mean power dissipated in the resistor. Then to increase the mean power dissipated in the resistor, it suggests that either the magnetic flux density or the angular speed of the coil could be doubled. Deduce the effect of each of these possible changes on the output of the coil. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work out power dissipated? Now in the previous question you just worked out EMF, which in this case is V. So we can say that power is equal to V squared over R. So you've just in the previous question worked out what V is. You've been given R, which is 6.8. So you do V squared over R and you get your answer out to be 0.38 watts. Now this next question is saying to us that the angular speed of the coil could be doubled, or the magnetic flux density could be doubled to increase your power dissipated. Now you've got to indicate firstly that if you double your magnetic flux linkage, so your magnetic flux density, because we know that EMF is equal to BAN omega. We know that if we double B, we'll be doubling V, we'll double in EMF, and we also know that if we double the angular velocity omega, we'll also be doubling EMF, because remember we said BAN omega is equal to EMF. So therefore if you double both of them, as the idea is that each one has a doubling effect, so the overall effect on EMF is going to be to the power of 4. But also note that if you double omega, it's spinning faster, so not only will it double the EMF produced, it'll also double the frequency of your alternating voltage produced. The next question says, figure 4 shows the arrangement that a student uses to investigate electromagnetic induction. The voltmeter connected across coil Y can be measured both positive and negative potential differences. The student opens the switch and the current in coil X decreases to 0 in a very short time. Describe what happens to the read on the voltmeter during this time. Go to explain why this happens. So pause the video now, then unpause the video when you want to go through your answer. Right, so it's the idea of our value, we're producing an EMF. So what's going on here? So we're getting a large EMF at first and then it's going to drop to 0. Why is that? Well, because we know EMF produced is related to the rate of change of flux linkage. So what would happen is if you open the switch and you reduce the coil so you reduce the current in coil X to 0, well, you're going to reduce the magnetic flux linkage, because when a current flows through the coil X, it will become an electromagnet and therefore have a magnetic flux field. So therefore what will happen is if the current is turned off, as it's an electromagnet, it is no longer a magnet, so the magnetic flux linkage will decrease to 0. So what will happen is, because there's a change in magnetic flux linkage via Faraday's law, that indicates to us we will induce an EMF, but ultimately that change disappears because it's going to stay at a value of 0. So because there's no change, therefore there's no EMF induced, so we will drop to 0. Now it's also important to note that with Lenz's law, it's going to be the opposite sign to the first reading, because what's happening is that the EMF is produced in the opposite direction to the change that caused it, so it's going to be a negative value. The next question says the arrangement shown in figure 4 can be used as a transformer when coil X is connected to an alternating current supply. Explain the reason for using a laminated core. So pause the video now, then unpause the video when you want to go through your answer. It's very important you can explain why we use laminated cores in transformers. Now laminations will reduce energy loss, so will increase the efficiency of a transformer. So it's important to note that this occurs because the laminations will reduce the size of eddy currents in the iron core. So that's a really important idea, because a lot of the inefficiency in a transformer is caused by eddy currents, currents of the magnetic field going in the opposite direction to the intended one. Okay, so the laminations will reduce that. Now remember, lamination just means to insulate with plastic. The next question, a student does an experiment to investigate electromagnetic induction. She drops a magnet vertically through a coil of wire. The coil is connected to a voltage sensor and a data logger is shown in figure 9. Explain why an EMF is induced as a magnet falls towards the coil. So pause the video now, then unpause the video when you want to go through your answer. Well, once again, how can we say there's an EMF induced? Well, EMF is induced when there's a change in magnetic flux linkage. That is Faraday's law. So as the magnet will fall through the coil, there will be an increase in the magnetic flux linkage, because now the magnet is inside the coil of the wire itself. The next question says, explain why V1 and V2 have opposite signs, because figure 10 shows a variation of the induced voltage V with time t after the magnet is released. The durations T1 and T2 and maximum values V1 and V2 of the two peaks are labelled. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, it's the idea that with Lenz's law, EMF is induced in a direction to oppose the change in flux linkage that produced the EMF. So what will happen is, as the magnet is going into it, it's going to produce a EMF in the opposite direction, a negative. However, then when it goes out of the coil, it's going to be producing a positive EMF, because now the magnetic flux linkage is decreasing. So we'll say that when it's increasing, when it enters, it's going to produce a negative EMF, and then as it leaves, it's going to produce a decrease in magnetic flux linkage is producing it, so therefore it's going to be a positive value. Remember, again, it's opposite values because of Lenz's law. Now the next question says, explain why the magnitude of V1 is less than the magnitude of V2, and explain why T1 is greater than T2. So pause the video now, then unpause the video when you want to go through your answer. Right, again, it's important. Why is V1 less than V2? Well, the magnet is going to go slower when it's entering because it's being dropped. So as it's falling, it's going to be accelerating due to gravity. So therefore, when it's going in, there's a smaller rate of change of flux linkage. So with Faraday's law, the rate of change of flux linkage is directly proportional to the EMF induced. Because it's going slower, there's a smaller rate of change. So therefore, a smaller EMF is going to be induced. Now, why is T1 greater than T2? Well, again, same reason. The magnet is accelerating downwards, so the time from the top of the coil to the center of the coil is going to be greater than the time from the center to the bottom of the coil, because it's going to be moving faster the more it's falling down due to the acceleration due to gravity. Now again, remember, EMF is going to be zero in the magnet at the center of the coil, because at that instantaneous moment there's going to be no change in flux linkage at that particular point. Now let's have a look at some questions on gravitational fields. So the first question says, a space mission is planned to remove a small boulder of mass 8.2 times 10 to the 3 kilograms from the surface of an asteroid. The gravitational field strength is 1.77 times 10 to the minus 4 newtons per kilogram at the surface of the asteroid. Calculate the weight of the boulder at the surface of the asteroid. Then explain why gravitational potential is always a negative quantity. And then the gravitational potential at the surface of the asteroid due to the asteroid's gravitational field is minus 3.99 times 10 to the minus 2 joules per kilogram. A spacecraft of mass 1.8 times 10 to the 4 kilograms removes the boulder to position when the gravitational potential is negligible. Calculate the work done against the asteroid's gravitational field. So pause the video now, then unpause the video when you want to go through your answer. Well, the first question is saying that weight is equal to mass times by gravitational field strength. So times your mass by a gravitational field strength and you get 1.45 newtons. Now, why is gravitational potential always a negative quantity? Well, like we've mentioned before, we define potential to be zero at infinity, because it's now outside of the gravitational field at infinity, so therefore there's no influence from the gravitational field on that object. So its gravitational potential and its gravitational potential energy is going to be zero. So therefore, because we've got to put work into the object to get to zero, because we've got to put energy in to get the object out the field, because gravity is always an attractive force, if we've got to put energy in to get to zero, the potential must be a negative value. Now the last question is, how do we work out the work done? Well, we know that the work done is going to be the mass of the object times by the change in gravitational potential. So what we can do is we can therefore say it's going to be 1.8 times 10 to the 4 multiplied by 3.99 times 10 to the minus 2. So therefore you can work it out to be 1050 joules. Now, how do we know that the change in gravitational potential is 3.99 times 10 to the minus 2? Because we know that at infinity the value of potential is zero, so the change is going to be from the value in the field to zero. The next question says the boulder will be placed in a circular orbit around the moon, so that the period t of the circular orbit of the boulder around the moon is given by the equation t equals the square root of 4 pi squared r cubed over gm. Then the orbital period of the orbit around the moon is 24 hours. The mass of the moon is 7.35 times 10 to the 22 kilograms. Calculate the radius of the orbit. So pause the video now, then unpause the video when you want to go through your answer. Well, it's important that when you're trying to derive the time period of a circular object, always remember a couple of things. Firstly, we can equate our centripetal force to that of the gravitational force, because the only thing that's causing a circular orbit is going to be the gravitational attraction between the moon and the boulder. Now, it is still a circular motion, so we can say it's the centripetal force. So we say the centripetal force is equal to the gravitational force. So we could use either mv squared over r or m omega squared r as our centripetal force. I think we'll use m equals omega squared r, and that equals g big M small m over r squared. The two smaller m's will cancel through, and then we can rearrange to therefore make t the subject. We might think, where has t come from? Well, we've got omega in our equation, and we know that omega is equal to 2 pi over t. That's an equation you've got to remember. Angular velocity is the change in angle, which is going to be 2 pi radians, over the time of one orbit, and then we can rearrange and make t the subject. Now, for the second question, what we've then got to do is use that previous equation. We've got to then say, well, we know what 4 pi squared is because it's just a constant. We know r cubed from the question. We know how far away it is. We know what the mass is because the mass of the moon is given in the question, and we know what g is. It's just a gravitational constant, so it's 9.75 times 10 to the 6. The next question says, one of the moons of Jupiter is named Io. The mass of Io is 8.93 times 10 to the 22 kilograms. The gravitational potential due to Io at its surface is minus 3.27 times 10 to the 6 joules per kilogram. State what's meant by a gravitational potential of minus 3.27 times 10 to the 6 joules per kilogram at the surface of Io, and show that the radius of Io is approximately 1.8 times 10 to the 6 meters. So pause the video now, then unpause the video when you want to go through your answer. So firstly, what's the definition of gravitational potential? Well, gravitational potential is the work done per kilogram. Then the second thing is that it's done from bringing a mass from infinity to the surface of Io, to the surface of the object. So therefore, we will say it takes 3.27 times 10 to the 6 joules to move every kilogram from infinity to the surface. Now remember, we always say it's from infinity to the surface of the object. Now then, how can you work out the radius of Io? Well, we know that gravitational potential is in this equation is V is equal to minus gm over r. Remember, it's always a minus value because gravitational potential is always a negative. We know what gravitational potential is. We know what the mass of Io is from the question, so therefore we can work out what r is because g is just a constant. Again, why do we use this equation? Because we've been given gravitational potential in the question. The next one says, one of the moons of Jupiter is named Io. The mass of Io, as we talked about before, is given to be 8.93 times 10 to 22 kilograms. A volcanic rock of mass 3 kilograms is ejected vertically upwards from the surface of Io with an initial velocity of 760 meters per second. The rock reaches a maximum height h above the surface of Io. Show that the rock's gravitational potential energy at height h is approximately minus 9 megajoules, and calculate the value of h. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So what we'd say is we're trying to work out the gravitational potential energy. Now we can say that it's going to be equal to a half mv squared, because what we'll say is that that kinetic energy is going to turn into gravitational potential energy. So we can say potential energy is equal to a half mv squared, and therefore what we can do is we can therefore link this in together. We can add our initial gravitational potential energy, because we know that it's obviously we've got the radius of Io from the previous question, so we can say that mgh from that part, and then you can add it onto the kinetic, and therefore you can work it out to therefore say 8.9 times 10 to the 6. Now then, how do you calculate h? Now it's very important here, because we've now projected it off the surface and the gravitational field strength has changed significantly. We can't use an equation from GCSE where we say potential energy is equal to mgh. What we've got to use now is we've got to use our more sophisticated equation, which is that gravitational potential energy is equal to g big M small m over r. We can then rearrange this and make r the subject. We know what E is from our previous question. We've got big M, the mass of Io. We've got small m, the mass of the rock. We've got E, we've got G because it's a constant, so we can work out r, which is our height going to be. But obviously, again, remember to subtract the radius of the moon from this because we're calculating h. Okay, so we'll subtract our radius of Io because we're working out the difference from the surface as opposed to the center of the system. So we get 1.8 times 10 to the 5 meters. The next question says, another rock of greater mass is ejected vertically upwards from the surface with the same initial velocity. State and explain how the height reached by the rock of greater mass compares to h. So pause the video now, then unpause the video when you want to go through your answer. So, what do we know? Well, the idea is the height will be the same, because as we should be aware, we're saying that the kinetic energy is going to be turning into the potential energy as it's being ejected vertically upwards. So if we said a half mv squared is equal to g big M small m over r, the two masses, the mass of the projectile is going to cancel through on both sides. So therefore it indicates to us that actually the mass of the object does not affect how high something will go up, and that's a very important idea in gravitational fields. The escape velocity of a gravitational field does not depend on the mass of the projectile, only the mass of the actual object producing the gravitational field. And because both of them are being ejected from Io, therefore the mass of the projectile does not make a difference. So that brings an end to our revision session today. I hope you've been successful and you've learned in today's revision session. If you have been, you should be able to answer A-level physics examination style questions. You can assess your understanding on A-level physics and understand what topics you need to improve upon for A-level physics. So thank you very much for watching this revision session on the paper 2 topics for AQA A-level physics based on the topics coming up on the 2022 physics examination. Thank you very much for watching and have a lovely day. Hello and welcome to this revision session for AQA A-level physics paper 2. So in this revision session, what we're going to be doing is looking at answering examination questions for A-level physics paper 2. So if we've been successful and we've learned in today's revision session, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and then finally understand what topics we need to improve upon for A-level physics. So how should you prepare for this revision session? Well, when you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the question in the revision session. When you're doing this, make sure you write in full sentences and show your full working out. Whilst in the right hand side, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. And at the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for AQA A-level physics? Well, the first step is learning the key facts. Use your revision guides, class workbooks, student prep notes and textbooks to learn the key ideas of the course. Now you might want to make mind maps or write out notes yourself to do this. The second step is to test yourself. Use Caboodle, Seneca, a student knowledge checker to quickly test your own knowledge, and you might wish to do this from your own cue cards. Then finally, you want to use examination prep books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work. And you may wish to even download your past exam papers to do this. So this process of learning the key facts, then testing yourself, then practicing examination questions is the way to prepare for AQA A-level physics. So let's have a look at a few questions now on thermal physics. So the first question says, a number of assumptions are made when explaining the behaviour of a gas using the molecular kinetic theory model. State one assumption about the size of the molecules. So pause the video now, then unpause the video when you want to go through your answer. Right, in this type of question, it's very important that you know all your assumptions of the molecular kinetic theory model, and also understand what assumptions are due to the molecules, what assumptions are due to the motion of the molecules, and what assumptions are down to the laws of physics that these molecules follow. So what do we know about the size of the molecules? Well, you've got to be aware that the volume of the gas molecules is negligible or much smaller than the volume of the gas itself. So you've got to understand that the molecules have a much smaller volume than the actual volume of the gas in itself. Now, it doesn't have a zero volume, it just means that the volume is much smaller or negligible. Now, we can also say this, that molecules are point masses, so we would say that we don't really consider their volume. The next question says, figure 1 shows how the pressure changes with volume for a fixed mass of an ideal gas. At A, the temperature of the gas is 27 degrees Celsius. The gas then undergoes two changes, one from A to B and then one from B to C. So firstly, calculate the number of gas molecules trapped in the cylinder using information from the initial situation at A. Then calculate in K the change in temperature of the gas during the compression that occurs between A and B. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, it says calculate the number of gas molecules. So straight away, we need to find an equation which has big N in the number of gas molecules. So what we'd say is PV is equal to NKT, where N is the number of gas molecules. You can then rearrange that, and you can then make N the subject. You say N equals PV over KT. Now, from the situation at A, we know what the temperature is, but we've got to convert it into kelvins by adding 273 to the value in degrees Celsius to get to 300. We know what the number K is, it's just a constant, and then we also know what P and V are because we can look on the graph, and at situation A we can determine the pressure in pascals and the volume in meters cubed. Remember, it's 10 to the minus 3, so when you say it's 0.70, it's 0.70 times 10 to the 3. Multiplying those values together gives you a number of 1.7 times 10 to the 22 molecules. As shown on the screen, another way of doing it is to work out the number of moles by doing N equals PV over RT and then multiplying your number of moles by Avogadro's constant, 6.023 times 10 to the 23. The next question is calculate the change in temperature during the compression that occurs. So what you would say is, you would say that in this situation, you know that T over V is going to be a constant. So we can say TB over VB is equal to TA over VA. And what we can know by that point is we know what the V for both A and B are. We know from the previous question what T is, which is, TA, so we can look from the graph, it's going to be 300 Kelvin. So what you can then do is say, well, obviously if TB over VB is equal to TA over VA, well, therefore TB is going to be TA times by VB over VA. Pop your numbers in and you get a value for TB of 214 Kelvin. At that point, it's asking to work out not what the temperature is at B, but rather the change in temperature from A to B. So you know that at A it's 300 and at B it's 214, so therefore our change is going to be 86 Kelvin. The next question says, deduce whether the temperature of the gas changes during the compression from B to C. Then compare the work done on the gas during the change from A to B with that from B to C on figure 1. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first question, how can we answer this particular question on about whether the temperature changes? So what you've got to consider is the idea that if the temperature remained constant, we would say that PC times by VC is equal to PB times by VB, because we know that for an ideal gas, when the temperature is constant, PV is going to be the same value throughout. That is linking into Boyle's law. So what you can therefore say is, therefore, if the temperature is constant, we can say that the pressure at C is equal to PB times by VB over VC. You'll then pop the value in, and then you can work out your answer by doing this 1 times 10 to the 5 times by 0.5 times 10 to the minus 3, their values given from the graph, divided by 0.3 times 10 to the minus 3, also another value given in the graph, to get 1.7 times 10 to the 5 pascals. But the point is the pressure at C therefore is higher than this, so this tells us that the temperature has to be different. So that allows us to conclude that the temperature isn't constant. Another way of doing it would be to work out what PB and P times by V at B is, and also P times by V at C is, and you'll notice that they're not equal, because when you do P times by V at point B, you will get 50, but P times by V at point C is 61, indicating that PV does not remain constant, so therefore T can't stay constant, because PV is only a constant when the temperature is the same. Now the next part is working out the work done on the gas. Now that links into the graph that you've got to the left hand side. Now the work done on a gas can be given by saying work done is P times by the change in V, or thinking about a PV graph, because we're doing P times V to work out our work done, it's going to be the area under the line, because the area under a line is always the y-axis times by the x-axis. So what you would do is you would calculate the area under the graph, but only a part of it, because it's asking for the work done during the change from A to B with that of B to C. So what you would do is you would work out the work done on the gas by looking at the area from A to B. So you work out that rectangular shape underneath the graph from A to B, and then you would also work out B to C, but what you would say is that B to C is the triangle but also the square. Now because there's a rectangular shape for A to B and for B to C, which from the graph they're going to be the same size, they will just cancel out. So therefore the total work done is just the area of the triangle. So you would do a half times by 0.5 times 10 to the minus 3 times by 1 times 10 to the 5 to work out our answer to be about 28 joules. Let's now have a look at a few questions on nuclear physics. So the first question says, explain in terms of binding energy why energy can be released when two nuclei undergo nuclear fusion. Then during the collapse of a supermassive black hole, helium-3 and oxygen-17 fuse to release energy. The equation for this reaction is helium plus oxygen goes to neon. So what we can do, table 2 gives us the date of these nuclei and therefore calculate in joules the energy released when this reaction occurs. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? It's all down to the definition of what binding energy is. So binding energy is going to be the energy that's needed to release all the nucleons from a nucleus. So what we can say is, why is energy released when two nuclei undergo nuclear fusion? Well, it's the idea that the total mass of the nuclei is more than the mass of the fusion product, i.e. when fusion takes place, mass is lost out of the actual system. So this tells us that the binding energy, or more correctly, the binding energy per nucleon increases when a nucleus is formed by a fusion, because therefore the molecule is more stable, so therefore it doesn't need as much energy for the molecules to exist there, so therefore our binding energy will increase. Now in this next question, what have you got to do? You're going to calculate in joules the energy released when this reaction occurs. So what you can remember is we can say E is equal to delta mc squared, where delta m is the change in mass. So the first thing to do is to work out the change in mass in this nuclear fusion process. So work out the mass before, which is the mass of the helium plus the mass of the oxygen, and then find the mass of the neon afterwards and find the difference between the two. We then get our mass to be 0.02272 by finding the difference given with the values in the table. At that point we can therefore turn that into kilograms by doing that value times by 1.661 times 10 to the minus 27 to get our value into kilograms. And by the way, that conversion factor is given to you in the equation book. Then we can say E equals mc squared to then work out our value of E, because C is 3 times 10 to the 8, and therefore we say the answer is about 3.4 times 10 to the minus 12 joules. The next question says, one model of nuclear fusion suggests that fusion happens when nuclei touch. Initially, the helium nucleus and the oxygen nucleus are separated so that the force between them is negligible. They move towards each other until they fuse. Fusion occurs when their centers are separated by a distance of 5.1 times 10 to the minus 15 meters. Figure 10 shows the initial positions and the final positions of the nuclei. Calculate the total change in electrostatic potential energy between the initial positions and the final positions of the nuclei. So pause the video now, then unpause the video when you want to go through your answer. Right, so what's important to note is how you can work out the potential energy from this particular situation. Well, what we know is that in this situation that the potential energy is going to be equal to 1 over 4 pi epsilon 0 times by Q1 Q2 over R. That's the equation from the electrical fields theory that gives us the equation for electrical potential energy. Now we know straight away what Q1 is, because we know that the charge on helium nucleus is going to be 2, because it has 2 protons, so it's 2 times 1.6 times 10 to the minus 19. Then we multiply by 8 times by 1.6 times 10 to the minus 19, because there are 8 protons in this particular oxygen nucleus. We'll then do over 4 pi times by epsilon 0, 8.85 times 10 to the minus 12, then times by R, which in this instance is the separation between the two nuclei, which is given in the question to be 5.1 times 10 to the minus 15 meters. So we get our answer to be 7.2 times 10 to the minus 13 joules. In questions like fusion and in Rutherford scattering, where you have electrostatic repulsion, it's always useful to be able to understand what the electrical potential energy formula is, so you can work out values based on this particular equation. The next question says helium can undergo fusion reactions with either sulfur or oxygen at the same temperature in a star. The nucleus has properties that depend upon its proton number and its nucleon number. These properties affect the fusion reaction. Discuss for this star how the properties affect the rate of fusion for sulfur and with helium compared to the rate of fusion of oxygen with helium. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, you've got to think about the charge and how it links to potential energy. So the idea is that doubling the charge will increase the potential energy or force needed to pull the nuclei together. Because if you think about it, it's Q1, Q2 over 4 pi epsilon 0 R. So if we're doubling one of the values of Q, we're going to have to double the potential energy needed. So this tells us that the actual nucleus with the larger charge, which is sulfur, because there's double the number of protons compared to oxygen, requires a greater kinetic energy between the particles, or a greater fusion pressure, and therefore that would decrease the rate of fusion. Now, it indicating as well that the larger radius of sulfur compared to oxygen means that the separation can be larger to fusion to take place as well. So therefore the idea would be that the separation can be larger for fusion to take place, so therefore increases the rate of fusion. So you've got to link both those factors in there. Both the amount of kinetic energy needed to overcome the repulsion is thought about, but also about the size of the nucleus themselves. The next question says, a thermal nuclear reactor uses enriched uranium as its fuel. This is the fuel in which the ratio of uranium-235 to uranium-238 has been artificially increased from that found in naturally occurring ore. Describe what happens when neutrons interact with uranium-235 and uranium-238 nuclei in a thermal nuclear reactor. So pause the video now, then unpause the video when you want to go through your answer. Well, this question is all about memory and knowledge and understanding. It's the idea that when a neutron interacts with uranium-235, it will absorb, the uranium-235 will absorb that neutron, so then the uranium becomes uranium-236 and will then undergo fission, and then will split and give out more neutrons to continue this fission process. Now, remember, the only neutron that can be absorbed by uranium-235 is a slow-moving neutron, or as it's given a name, the thermal neutron, because it's in thermal equilibrium with its surroundings. Whilst when a neutron hits a uranium-238 or interacts with the uranium-238, it will be the uranium-238 absorbs or scatters the neutron and actually becomes plutonium, working it through eventually, so it doesn't carry out fission straight away. The next question says the amounts of uranium-235 and uranium-238 in the ore decrease due to radioactive decay at different rates. A sample of uranium ore today contains 993 grams of uranium-238. The mass of uranium-238 in this sample was greater 2.00 times 10 to the 9 years ago. Show that the mass of uranium-238 in this sample at this time was about 1.4 kilograms. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, we're looking at how the number of nuclei, or the mass of the radioactive material, has decreased over time. So we've got to use the equation which looks at radioactive decay. So what we'd do is we'd use the equation of N is equal to N0 times by e to the power minus lambda t, where lambda is our decay constant, time is the time in this particular decay, and n0 is the number of radioactive nuclei at the start. So what you do is you pop your values in, because you've got straight away the value of the decay constant, which is 1.5 times 10 to the minus 10. You got the value of t, which is 2.0 times 10 to the 9 from the question, and the question is asking you to work out what the mass is going to be at that particular time. So what you would therefore do is therefore say you can ratio n0 over nt, and therefore you get a value of about 1.36. So that tells us that we're at 993 grams now. So if you convert that to kilograms, so it's 0.993, multiply that by 1.36, my apologies, to get your value to be 1.35 kilograms. Another way of working it out will be to work out the number of half-life that takes place in the particular time period, because we know that the decay constant is 1.54 times 10 to the minus 10 years to the minus 1, so we can work out what our half-life is going to be, or by doing half-life is going to be equal to the decay constant over log 2, so you can work it through like that, and you work out that the number of half-lives is going to be 0.44. So when you work it through like that, because there's only been 0.44 half-lives, you work back to see how much you have at the beginning. So it's going to have 1.36 times more than it does now, so 1.36 times by 0.993 is equal to 1.35 kilograms. The next question says a thermal nuclear reactor requires a minimum of 3% of its uranium mass to be uranium-235. The ratio of uranium-235 to uranium-238 in the ore has changed over time. 2 times 10 to the 9 years ago, the sample contained 52 grams of uranium-235. Deduce whether the sample had enough uranium-235 content to be used in a reactor 2 times 10 to the 9 years ago. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, we've got to find the ratio of this of uranium-235 compared to the total value. So you say the ratio is going to be the number of uranium-235 over the number of uranium-235 plus uranium-238. Now from the question we know that uranium-238 is going to be 1,400 grams, because we know in the previous question it was 1.4 kilograms. We know that the mass of the uranium-235 is 52. So therefore we can work out our ratio to be what that particular value is. So therefore you'd work it out to be approximately 52 over 1,400. So therefore it's going to be between 3.7 and 3.9%, which is much higher than 3%. So we give our conclusion, we answer the question that's being asked, and we say that yes, it must be able to carry out this fission process, because it's above the minimum required percentage of 3%. The next question says, a thermal nuclear reactor uses a moderator to lower the kinetic energy of fast-moving neutrons. Explain why the kinetic energy of neutrons must be reduced in a thermal nuclear reactor. Then, as a result of a collision with an atom of a particular moderator, a neutron loses 63% of its kinetic energy. A neutron has an initial kinetic energy of 2 mega electron volts. Calculate the kinetic energy of the neutron after 5 collisions. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? So what we're talking about is the role of the moderator in the nuclear fission process. So what we say is to increase the probability or the chance of fission, which occurs when a neutron collides with uranium-235. Well, therefore, what we need is we need to have our moderator lower the kinetic energy, so therefore our neutron is a thermal neutron and a much slower moving neutron, and that will allow the neutron to be absorbed by uranium-235. So the moderator reduces the kinetic energy of the neutron, so therefore it will be more likely to be accepted by the uranium. Now the next question is asking us to work out the kinetic energy after five collisions. So what you can do is a little bit of a trick. So what we can say is, if we're losing 63% each time, we can say the energy at the end is going to be 1 minus 0.63 times by the energy at the start, or the energy of the incident. Now 1 minus 0.63 is 0.37. So each time you're pretty much saying you're going to be left with 37% of what you started with. So what you can therefore do is, if you want to do this 5 times, you would then get this 0.37 and take it to the power of 5. So what you say is you go, the energy at the end is 0.37 to the power of 5, because there are 5 different collisions, so it happens 5 times, multiplied by the energy at the start. Now the question tells you that the energy at the start is 2 times 10 to the 6 electron volts. Remember, it says 2 mega electron volts, and mega means times 10 to the 6. So we therefore do that times by 0.37 times 10 to the 5, and we get 1.4 times 10 to the 4 eV. The next question says the kinetic energy of a neutron in a thermal nuclear reactor is reduced from about 2 MeV to about 1 eV. Explain why the number of collisions needed to do this depends on the nuclear number of the moderator atoms. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, a link has to be made between the change of kinetic energy of the masses, okay, involved in the collision with that particular momentum. So it's the idea that a nuclear number in the nucleus increases more as the nuclear number increases in the nucleus, more collisions are required to make this take place. So the idea is more kinetic energy is lost when the mass of the moderator is closer to the mass of the neutron. That's because of the idea of the conservation of momentum. So therefore the number of collisions needed increases with the nuclear number, because there's a greater difference between the two values. So when you think about the conservation of momentum, when you have much more different masses, the energy lost out of each collision will be less, so you need them to be of similar sizes. The next question says, one fission process which can occur in a thermal nuclear reactor is represented by the following equation. Calculate in MeV the energy released in this fission process. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work out the energy released in MeV in this fission process? So the first thing you do is, because you're given the masses in this particular question, you find the mass differences before and after. So you do the mass of the uranium plus the mass of the neutron, then subtract the mass of the xenon, the mass of the strontium, and the mass of the 4 neutrons from that value. So as you can see on the screen, we've worked out the mass before and then subtracted the mass afterwards. That gives us a value of 0.180 U, where a U is an atomic mass unit. So what you can therefore do is take a shortcut and therefore say 1 U, which is a mass unit, times by 931.5 will turn into the value into an energy unit of MeV. That's just a conversion factor, which is a very useful factor to be able to understand and use. So when we do 0.18 times by 931.5, we get 168 MeV, which is the energy released in this fission process, because that's the difference in mass. So the mass of 0.180 U is turned into an energy of 168 MeV. Let's now have a look at a few questions on magnetic fields. So figure 7 shows a search coil positioned on the axis of an electromagnet with the plane of the search coil perpendicular to the axis. A magnetic field is produced by a constant current in the electromagnet. Assume that the magnetic flux density inside the search coil is uniform. The distance between the search coil and the end of the electromagnet is x. Figure X shows how the magnetic flux density B of the field varies with x. So the search coil has 200 turns with a cross-sectional area of 3.5 times 10 to the minus 5 meters squared. The search coil is placed at x equals 0.070 meters. Show that the magnetic flux linkage through the search coil is about 5 times 10 to the minus 4 Webers. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? Well, the first thing you can do is you can look at the graph, and you can indicate from the graph straight away that the magnetic flux density B at a value of 0.070 meters is equal to about 0.07 Teslas. We can then look at the equation sheet at the back of the book, and we can see that magnetic flux linkage N phi is equal to BAN. So we've got B from the graph, we've got A from the question, and we've got N from the question as well, because N is the number of turns and A is the cross-sectional area. So therefore works out to be about 4.9 times 10 to the minus 4. The next question says the search coil is now moved at a constant speed of 0.80 meters per second along the axis so that x is increasing, and EMF is induced across the terminals of the search coil. Explain what happens to the value of EMF as the search coil moves. Then the search coil passes through the position where x equals 0.10 meters. Deduce whether the EMF can exceed 5 millivolts for values of x greater than 0.10 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, well, the first question, it's all about explaining how EMF is generated. So the point is, as the coil moves, there's a rate of change of magnetic flux linkage through the coil. Now, when you've got a rate of change of flux linkage, that will induce an EMF in that particular conductor. So the induced EMF that's produced is therefore proportional to the rate of change of the flux linkage, which is Faraday's law. So therefore, as the rate of change is going to decrease as it's moving through, that tells us that the EMF produced is going to decrease as well. Now the next question is deduce whether the EMF will exceed 5 millivolts for values of x greater than 0.10 meters. So what we've got to do is we've got to find the change in the magnetic fields, or the magnetic flux, okay, with the distance. So what you would do is that's going to be the gradient of the line, but the issue is this line is a curve. So to find the gradient of this line, you've got to draw a tangent in. So when you draw your tangent in, you can then find your value of what is going to be b over x, and therefore you can use that to therefore work out values of EMF with the idea of EMF is equal to n delta BA over delta t, and work out values this way. So what you can therefore do is, let's say at a value of x equals 0.10 meters, we do b over x and we get 0.095 over 0.137, which is 0.69. Therefore we can substitute this into Faraday's law and work out our value, which should be about 3.8 times 10 to the minus 3 volts, or 3.8 millivolts. The next question looks at gravitational fields. So, the Global Positioning System, GPS, uses satellites to support navigation on Earth. One GPS satellite is in a circular orbit at height h above the surface of the Earth. The Earth has mass m and radius r. Show that the angular speed of omega of the satellite is given by omega is equal to the square root of g m over r plus h all cubed. Then calculate the orbital period of the satellite when h equals 2.02 times 10 to the 7 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, it's the idea that in a satellite in a circular orbit, that the centripetal force which is causing a circular orbit is going to be equal to the gravitational force, because it's a gravitational force of attraction between the Earth and the satellite which is causing it to go in an orbit. So we can equate the two to each other. So we can say that gmm over r squared, the gravitational force between two objects, Newton's law of gravitation, is equal to mr omega squared. Now why do we use omega squared here and not mv squared over r? Well, it's because the question wants you to derive it in terms of omega, so it seems sensible to use that particular equation for centripetal force. We then rearrange it and we get our value out to be the one given in the question. The next question says calculate the orbital period of the satellite when h equals that particular value. So what it tells us is we've got the radius of the Earth from the examination equation book, we've got h in the question, we've got g, we've got the mass of the Earth because it's given to us in the equation book, so therefore we can work out omega. So we can work out omega by substituting all those terms into this particular equation, and we get 1.45 times 10 to the minus 4 radians per second. We can therefore say that time period is equal to 2 pi over omega. You need to know that that's just a fact. So therefore 2 pi over the value you just calculated gets you 4.3 times 10 to the 4 seconds. The next question says figure 3 shows the orbital plane of the satellite inclined at an angle to the equator. X, Y and Z are locations on the Earth. X is at the North Pole, Y is on a high mountain and Z is on the equator. The satellite is to be launched from one of the locations. State and explain which launch site, X, Y or Z, minimizes the amount of fuel required to send the satellite into its orbit. So pause the video now, then unpause the video when you want to go through your answer. Right. So you've got to think about which one are you going to go without the energy being dissipated as it goes up into orbit. because you've got to think about the amount of fuel required links to how much energy needs to go up in there, so you don't want much dissipated. So what you would do is you'd launch from Z with some speed or some energy. Now the reason why in some speed or some energy argument, in the sense of you can talk about why this is in terms of the energy. So you can say that, oh well, half mv squared is equal to gmm over r, so therefore you can work it through and you can show that actually with Z it's going to be the best place, because if you think about it, it's going to have the largest kinetic energy or the largest initial speed from the Earth's rotation, because at that center it's going to have the greatest amount of kinetic energy from the Earth's rotation. The next question says, a satellite has a mass of 1,630 kilograms. Calculate the gravitational potential energy of the satellite when it's in orbit from the previous question. Then a different satellite is in a higher circular orbit. Explain how the linear speed of the satellite compares with the linear speed of the satellite in the previous question. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to work out the gravitational potential energy, and you can work that out by doing G big M small m over r, because to work out the gravitational potential energy you've got to do the gravitational potential G big M over r multiplied by the mass of the actual object moving in the gravitational field. Now you know what big G is, it's a constant given on the equation sheet. You know what the mass of the Earth is, big M, and you know what the mass of the satellite is because it's given in the question. You know what the value of r is, once again, because you know the orbital distance from the center of the Earth, so it's 2.66 times 10 to the 7, which allows you to work out a value of minus 2.44 times 10 to the 10 joules. Remember, it's a minus value because all gravitational potential energies when in a field are going to be a minus value. The next question is talking about what happens to the linear speed of the satellite when it's in a higher orbit. Well, what you've got to remember is we can say for orbital speed a half mv squared is equal to gmm over r, or you could also say to yourself that the centripetal force is equal to the gravitational force, so it's a half mv squared over r, half mv squared. It's going to be F equals mv squared over r, which is therefore equal to g big M small m over r squared. So at that point you can rearrange it, and what you can say from this is V is equal to the square root of gm over r. So what it's telling us is, because g and big M are going to be constants, that V is going to be directly proportional to 1 over the square root of r. So when you've got a bigger value of r, because you're in a higher orbit, this is going to give us a smaller value for V. So when you get higher up in the gravitational field, the linear velocity gets smaller. The next question says, figure 2 shows a moon of mass m in a circular orbit of radius r around a planet of mass m, where small m, the mass of the moon, is much smaller than the mass of the planet, big M. The moon has an orbital period t, and t is related to r by the equation t squared is equal to k r cubed, where k is a constant. So firstly, show that k is equal to 4 pi squared over gm. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, once again, we know that because it's an object undergoing a circular orbit, that the gravitational force gmm over r squared is going to equal the centripetal force mv squared over r, or rm omega squared. So what we can therefore say is we can work out our values and say that, well, if gmm over r squared is equal to mr omega squared, well, therefore by that logic you can say that g big M over R is going to therefore equal omega squared. Now we also know that omega squared is equal to 2 pi over t squared over everything squared, so it'll be 4 pi squared over t squared. Substitute that in, and we can therefore work everything through, and we get our value for t squared to be equal to 4 pi squared over gm all times by r cubed. Now that k is the proportionality constant between t squared and r cubed, so therefore we can equate everything next to r cubed to be equal to k, which is 4 pi squared over gm, as stated in the question. The next question gives us data for 2 of the moons of the planet Uranus. Firstly, calculate the orbital radius x of Umbriel, and then secondly, calculate the mass of Uranus. So pause the video now, then unpause the video when you want to go through your answer. Right, how do you answer this first question? Well, it's important to know that when we're doing this, we can say that t squared is proportional to r cubed. So what we can say is that t squared over r cubed for both of them is going to equal out. So what we can therefore do is rearrange it and make r of Uranus, okay, because which is the question we need, because we're trying to work out the orbital radius there, is going to be equal to the radius of the moon times by tu over tm times by the power of t to the 2 to a third. 2 over 3, or 2/3. Sorry about that. So therefore you pop your values in. So what's the radius of the of m there? So we're going to say that it's going to be 1.2 times 10 to the 8, which is given in the question. What's our value for t for Umbriel? Well, it's given there. It's 4.14 divided by the time period for Miranda, which is 1.41, all to the power of 2/3. You can work out your value to be 2.6 times 10 to the 8. So what, you don't have to change any of the units from days into seconds, because we're just ratioing the values, so you can just keep them in days. Now the next question is calculate the mass of Uranus. Now we've previously in the previous question said that, well, t squared is equal to 4 pi squared over gm times by r cubed. Now what we can therefore do is rearrange this and make big M, because we're trying to work out the mass of Uranus, to be the subject. So we'd say 4 pi squared over t squared g times by r cubed is going to give us a value. Now here, because we do want to get a mass in kilograms, we need to have a time in seconds. So when we're doing this for Miranda, okay, for example, we can work out that the time in seconds for Miranda is going to be 1.41 days. We do 1.41 times by 24, the number of hours in a day, times by 3,600, the number of seconds in an hour, to give us the number of seconds to be 1.22 times 10 to the 5 seconds. We can then substitute all the values in, and we can get our values out to be 8.5 times 10 to the 25 kilograms. The next question says, from the data for the moons of Uranus, deduce which moon in table 3 has the greatest escape velocity for an object on its surface. Assume the effect of Uranus is negligible. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you should do is, you could work out the escape velocities for each object, or you could do a little bit of a mathematical trick to speed the process up. So we can say, to work out escape velocity, we can say that it's going to be the potential energy equals the kinetic energy for our escape velocity, so it's gmm over r is equal to a half mv squared. Now remember, instead of using r, we could maybe use diameter over 2. Why is that? Well, because we're given diameter in the table, so it makes sense to use that. So if we rearrange it and make v the subject, the escape velocity of the subject, we'll rearrange it and see that the escape velocity is equal to 4gm over d, all to the power of a half, which is the square root. So therefore we can say v is equal to the square root of 4gm over d. So this tells us that ultimately that the escape velocity is going to depend upon the square root of m over d. So what you can therefore do is, you've got the mass of each of the moons, you've got the value of d for each of the moons, the diameter, and you know you can just square root each of the terms. So what you would do is you do m over d for each of them and square root them. You then work out quite quickly that that Titania is going to have the highest value for that, so therefore it's going to give the highest escape velocity. The next question says, a spring mechanism can project an object vertically to a maximum height of 1 meter from the surface of the Earth. Determine whether the same mechanism could project the same object vertically to a maximum height greater than 100 meters when placed on the surface of Ariel. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? Well, it all links into the strength of gravity on each of the planets. So the first thing you can do is, you know already the strength of gravity on Earth, 9.81, but what's going to be the strength of gravity on Ariel? So we know that G is equal to gm over r squared, where G is a constant and big M is going to be the mass of the object, in this case Ariel, and we know that r squared in this case is going to be the radius of the planet, because we're thinking of the surface of the planet, planet is where it's been projected off, so therefore the separation from the centre to the surface is just the radius of the planet, which again is given to you in the question in the table, but you've been given the diameter, so you do diameter over 2. So therefore you can say that G for Ariel, when you work it all through, is 0.25 meters per second squared. Now what we can therefore do is equate the two of mgh on Earth to mgh on Ariel. Now if you notice, m on both sides cancels through because it's the same value, it's the same mass of the object. So therefore we can say gh on Earth is equal to gh on Ariel. So we know the height on Earth is going to be 1.0 meters, because it tells you in the question. We know that the strength of gravity on Earth is 9.8, so therefore we can say 9.8 times by 1 equals 0.25, the gravity on Ariel times by this height. And when we work it through, height is therefore going to equal 40 meters, so it won't go higher than 100 meters. The next question says, firstly, define the gravitational potential of a point. Then figure 2 shows the positions of equipotential surfaces at different distances from the centre of the moon. Firstly, explain how the equipotential surfaces in figure 2 show that the gravitational field is not uniform. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first one is just a definition of gravitational potential, and there are a few key words you've just got to know. It's the work done or the energy required in bringing a 1 kilogram mass or a unit mass from infinity, from outside the field, into a point inside the field. Now, how do you then explain equipotential surfaces in this figure 2 so the gravitational field is not uniform? Well, you can see about the gravitational field strength from the potential difference between the lines, okay, of equipotential in the field. So you can see straight away that the potential differences between the lines is constant, but the distances are not. So this tells us when we do delta V over delta R, what we call the potential gradient, well, that the potential gradient is changing as you're moving through the field. Now the potential gradient, delta V over delta R, is the gravitational field strength, so therefore it tells us that the gravitational field strength is not going to be constant. You could also link it into the fact by saying the equipotential surfaces are not straight, they're curved, so therefore there's going to be a variance because there's a curvature in the field. The next question says, calculate using figure 2, which was shown previously, the escape velocity at the surface of the moon. And the radius of the moon is 1.74 times 10 to the 6 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, once again, as mentioned, what we do is to work out the escape velocity. We got to say that G big M small m over R is equal to a half mv squared. The potential energy, Gmm over R, is equal to the kinetic energy, a half mv squared. That's how we can, that's the condition we have to work out the escape velocity. So therefore we can say the escape velocity, when we rearrange this, is the square root of 2gm over R. Now we've got G because it's a constant. We've got R because we know it's from the surface of the, it's going to be the surface of the particular value there, so you can work it through. So you, in the previous question, you were told what the value, the radius of the moon was, 1.74 times 10 to the 6 meters, so you can pop that in as R. However, we don't have the mass of the moon, so how can you work out the mass of the moon? Well, we can say that that the potential is going to be equal to Gm over R, so therefore we can work backwards and say, well, M is equal to minus VR over G. Remember, it's minus because there's got to be a negative potential, because there's a gravitational field which is attractive. So you pop your values in of V, R and G and you get 7.3 times 10 to 22 kilograms. You pop that into that previous equation and you get 2.3 times 10 to the 3 meters per second. Let's now have a look at a few questions on electrical fields. So, figure 3 shows an arrangement used to investigate the repulsive forces between identical charged conducting spheres. The spheres are suspended by a non-conducting thread. Each sphere has a mass of 3.2 times 10 to the minus 3 kilograms and a radius of 20 millimeters. The distance d is 40 millimeters. The capacitance of a sphere of radius r is 4 pi epsilon 0 r. Each sphere is charged by connecting it briefly to the positive terminal terminal of a high voltage supply, the other terminal of which is at 0 volts. After this has been done, the charge on each sphere is 52 nanocoulombs. So calculate the potential of one of the spheres. The charged sphere in figure 3 are in equilibrium. Draw arrows labelled to show the forces on figure 3 on sphere B, then suggest a solution of one problem involved in the measurement of D in figure 3. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, straight away we can say that the capacitance of the object is equal to 4 pi epsilon 0 r. Now we know what r is because we've got the radius of the sphere. It's going to be 0.020 meters because we turn 20 millimeters into meters. So we can say that the capacitance is 2.2 times 10 to the minus 12 farads. Now we know from the definition of capacitance that the capacitance is going to be equal to charge over volts. Okay, so we can rearrange that and say volts or voltage is equal to charge over capacitance. We've got the charge of 52 times 10 to the minus 9 for that particular sphere because it tells you in the question. We then divide that by the charge, which we know to be, sorry, not the charge, the capacitance, my apologies, by 2.22 times 10 to the minus 12 because you just worked that out. So therefore V is equal to 23,000 volts. Now because the charged spheres are at equilibrium, what we can say is that we've got a weight acting from the center vertically down for each of them because they've got a mass. Now you've got electrostatic force or repulsion to the right starting from the inside edge of the sphere for B because it's being repelled by A because they've got the same charge, so it's pulling away. And then finally for B there's a tension label parallel to the thread and it's going to be upwards because the actual thread itself is taut, so it's pulling up the sphere B with this at the same angle at which the string is, so therefore you need all three arrows to get your marks. Now one solution to the problem involved in measuring D, which is the distance between the two spheres. Well, what problems could there be? Well, if you've got a conducting metallic instrument such as like a metal ruler placed between the two spheres, it'll affect the separation because of the movement of charge due to that conductor. So therefore you're going to have to use something like calipers or a ruler which is made of a non-conductor material. Or you could say that another problem could be that if you physically have the spheres touching each other, or you have touched them and you've taken your measurement, that can alter the reading because the charge has been discharged through you. You could also talk about the difficulty of measuring curved objects. It's difficult to measure the straight line distance between two curved objects. So what you could do is also as well that if you read a ruler behind the spheres, it's going to give you a parallax error. So you've got to think about maybe using a ruler and a set square to line up the ruler with the sphere so you don't get that parallax error. The next question says, show that the magnitude of the electrostatic force on each sphere is about 4 times 10 to the minus 3 newtons. Then a student measures the angle theta when the apparatus in figure 3 is at equilibrium. The student records theta is 7 degrees. Discuss whether this measurement is consistent with the other data in this investigation. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first particular question? Well, what is the force on this object? Well, it's the electrostatic force as given in the question. How do you calculate the electrostatic force? Well, Coulomb's law tells us it's Q1 Q2 over 4 pi epsilon 0 r squared. Now the distance, which is the separation between the two charges, is going to be 80 millimeters. Why is that? Because we go from the center of one charge to the center of the other charge. Now each charge has got a radius of 20 millimeters, so there's 20 millimeters from the center to the edge of the sphere, and also the distance between the two objects themselves is 40 millimeters, so therefore the total distance from center to center is 80 millimeters. So we can use the value of r in this one to be 0.080 meters because we convert from 80 millimeters into meters, and then the charge of both of them is the same. So Q1 Q2 is going to be 52 times 10 to the minus 9 times by 52 times 10 to the minus 9 because we've got it from nanocoulombs into coulombs. So we pop our values through because 4 pi epsilon 0 is a constant, and we get 3.8 times 10 to the minus 3 newtons. Now the next question says, discuss whether the measurement of theta is 7 degrees is consistent with other data in the investigation. Well, what we know is when each sphere is in equilibrium, we can use our trigonometry to say that, well, tan theta is going to be equal to the electrostatic force divided by the weight. Well, why would that be? Well, if you think about it, okay, when you draw your right angle triangle of forces on the object, you've got the tension, okay, which is acting in the in the same direction as the string is being taut. You've got the weight acting vertically down, and you've got the electrostatic force acting horizontally in this situation. So when you draw your right angle triangle of forces, you'll realize quite quickly when you draw in theta that in this particular situation the opposite to theta, the opposite to the angle, is going to be the electrostatic force, because that's in the horizontal. We know that the adjacent is going to be in the vertical, which is going to be the weight. So therefore we can say tan theta is equal to opposite over adjacent, so it's going to be equal to electrostatic force over the weight. So it's 3.8 times 10 to the minus 3, the electrostatic force, over the mass of the object, 3.2 times 10 to the minus 3 kilograms, times by the strength of gravity, 9.8. Then we do inverse tan of that, which is 6.9 degrees. So hopefully you've enjoyed this particular revision session on paper 2 for AQA A-level physics. If you've been successful and you've learned in today's revision session, you should be able to answer A-level physics examination style questions, assess your understanding on A-level physics, and understand what topics you need to improve upon for A-level physics. So thank you very much for watching this video on paper 2 revision for AQA A-level physics, based on the 2022 Advanced Information Guidance on what topics will be on the examination. So thank you very much for watching and have a lovely day. Hello and welcome to this revision session on paper 2 for AQA A-level physics. So what we're going to do in this revision session is we're going to look at answering examination style questions for A-level physics paper 2 for AQA. So if we've been successful and we've learned in today's revision session, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So how should you carry out this revision session? Well, when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. And when you're doing this, make sure you write out in full sentences and show your full working out. Whilst on the right hand side in this section, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. And at the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising AQA A-level physics? Well, the first step you should be doing in your revision is learning the key facts. So use revision guides, class workbooks, student prep notes, a textbook to learn the key ideas of the course, and you might wish to make mind maps or write out notes yourself. Then secondly, test yourself. Use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Then finally, in the step 3 is use exam prep books, homework books, supervised study books, workbooks to answer exam questions and then mark your own work, and you may wish to download your own examination past papers to do this. So the steps of learn the key facts, testing yourself and practicing exam style questions is the way to revise AQA A-level physics. So let's start off by looking at thermal physics. So in the following question it says figure 1 shows how the temperature of water is maintained in a hot tub. The hot tub system has a volume of 4.5 meters cubed and is filled with water at a temperature of 28 degrees Celsius. The heater transfers thermal energy to the water at a rate of 2.7 kilowatts while a pump circulates the water. Assume no heat is transferred to the surroundings. So calculate the rise in water temperature that the heater could produce in 1 hour, and then the pump can circulate the water at different speeds. When working at higher speeds, the rise in temperature is greater. Explain why. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular first question? Well, you've got to remember what our equation is when we have a temperature rise in a situation, and that is that we would say that E equals MC triangle T. Now, we want to here work out triangle T, so what we would do is we'd rearrange this and we'll make triangle T the subject. So you can see quite clearly that triangle T, or delta theta as is written down here, is equal to E over times by c. Now it's important to note that in this particular question you're given the power and you're given the time, so we can use this to work out what the energy is, because we should know that energy is equal to power times by time. But there are two issues with this particular question. Firstly, time is given in hours, so you've got to convert that into seconds by doing 60 times by 60, because we work in seconds in physics, not in hours. And then secondly, you're given the power in kilowatts, so you've got to once again convert that into watts by saying it's 2.7 times 10 to the 3, because kilo means times 10 to the 3, to then work out what your power is, and energy equals power times by time, so you can work that energy out. We know what our value for C is because it's given in the question, 4,200, and we know what our value for the mass is because once again it tells you that the volume of water is equal to 4.5 meters cubed, and in the question it tells you that the density is 1000. So therefore you can say that because density is mass over volume, well therefore mass is density times volume, so you can work it through, pop all the numbers in, and you get an answer to be 0.51 Kelvin. Now how can when working at higher speeds the rise in temperature be greater? Well, you've got to think about what's going on, because when the pump is working and it's pumping the water around, the pump is doing work on the water, it's putting energy into the system. So what this means is that this work can raise the temperature of the body because of the first law of thermodynamics. Energy is going into the situation and it's not changing state, so therefore it must be the kinetic energy store of the object which is increasing, so therefore that is shown as the temperature of the body. Also you can say that this links in because we know that the mean squared speed is directly proportional to the temperature. We know that from the equation given in the equation book, so we can say that when the mean squared speed goes up as indicated in the question, that the temperature must go up as well. Let's now have a look at some questions to do with nuclear physics. So the first question says an alpha particle with a kinetic energy of 4.9 MeV is directed towards the center of a gold nucleus of radius r, which contains 79 protons. The alpha particle is brought to rest at point S, a distance r from the center of the nucleus is shown. So firstly calculate the electrical potential energy in joules of the alpha particle at point S, and then secondly calculate the distance of closest approach of the alpha particle to the nucleus. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, what you've got to remember is that we would say in this situation the kinetic energy of the alpha particle is turned into the electrical potential energy when it is repelled by the gold nucleus, and it will be repelled because they're both positively charged. So we can say that if you're starting off with 4.9 MeV of kinetic energy, then it's going to turn into 4.9 MeV of electrical potential energy. But the issue is it wants the energy to be in joules, so the question's pretty much asking you to convert from MeV into joules, and we know that 1 eV is 1.6 times 10 to the minus 19, so therefore 1 MeV is 1.6 times 10 to the minus 13, because M means times 10 to the 6, so you would do 1.6 times 10 to the minus 13 times by 4.9 to get 7.8 times 10 to the minus 13 joules. Now, to work out the distance of closest approach, what you've got to remember is that electrical potential energy is charge times by electrical potential, and electrical potential is Q over 4 pi epsilon 0 r. Both equations are given in the examination booklet. So therefore we can say that electrical potential energy is going to be Q1 times by Q2 over 4 pi epsilon 0 r. We can then rearrange it and make r the subject, so say r is Q1 Q2 over 4 pi epsilon 0 times by electrical potential energy. Now in the previous question we worked out the electrical potential energy in joules, so we can pop that into the equation. Now we know that the charge of the object is going to be, for the alpha particle, if you notice, it's going to be 2 times by 1.6 times 10 to the minus 19, because there are 2 protons in the alpha particle, and then for the gold nucleus it tells you there's 79 protons, so it's 79 times by 1.6 times 10 to the minus 19, because remember each proton has a charge of 1.6 times 10 to the minus 19. Pop the values in and you get your answer to be 4.67 times 10 to the minus 14 meters. The next question says, determine the number of nucleons in the gold nucleus, where you're given the radius in R0. Then it says the target nucleus is changed so it has one fewer proton. The alpha particle is given the same kinetic energy. Explain without further calculation any changes that occur to the distance r and ignore any recoil effects. So pause the video now, then unpause the video when you want to go through your answer. Right, so this question is asking you to use the equation r is equal to r0 a to the power of a third. Now in this question you're given r and you're given r0, so at this point you need to work out a. So you would say that a is equal to r over r0 to the power of a third. We'll just rearrange the equation and we'll work out our value through to be a to be equal to 197. Now a is the number of nucleons, so that is your answer. Now, in this next question, what's going to happen to the distance of closest approach? Well, if we think about it, we're saying r is equal to q1 times by q2 over 4 pi epsilon 0. So just from thinking of that calculation, if the value on the top, q1 times by q2, is going to be lower because one of them has less protons, okay, that tells us that our value for r is going to decrease. Now if you think about it in terms of kinetic energy, well, if there's less protons in the nucleus, then there's going to be less of a repulsive force between the nucleus and the alpha particle, so therefore it can travel further, okay, before the repulsive force causes the same kinetic energy to turn into electrical potential energy. The next question says, the core of a thermal nuclear reactor contains a number of components that are exposed to moving neutrons. State what happens to a neutron when it's incident on the moderator. Say what happens to a neutron when it's incident on a control rod. And then a slow moving neutron is in collision with the nucleus of an atom of the fuel which causes fission. Describe what happens in the process. So pause the video now, then unpause the video when you want to go through your answer. Right, so what happens when a neutron is hit by a moderator? Now it's important to know what the role of a moderator is. The moderator is there to slow the neutron down so it can be absorbed by other fissile nuclei. So what happens is the neutron will undergo an elastic collision and bounce off the moderator with less kinetic energy. That's a very important idea, that the moderator slows down the neutrons via collisions. Now you've got to understand that a control rod works because it will absorb a number of the neutrons to stop them from encountering any more fissile nuclei. So what happens with the control rod is that the neutron is absorbed. Now in the next question it says that a slow moving neutron is in collision with the nucleus of an atom of the fuel which causes fission. What will happen? Well, you've got to think about the different steps. So the first step is that the neutron is absorbed by the nucleus, so a uranium-236 nucleus is formed. This then causes the unstable nucleus to fission, and that produces several nuclei, and it also releases some fast-moving neutrons, and some energy is released as gamma photons. The next question says, a thermal nuclear reactor produces radioactive waste. So state the source of this waste and discuss some of the problems faced in dealing with the waste at various stages of treatment. So your answer should include the main source of the most dangerous waste, a brief outline of how waste is treated, and then problems faced in dealing with the waste, suggestions for overcoming these problems. So pause the video now, then unpause the video when you want to go through your answer. Right, for this type of question, because it's a 6-mark question, you should really try and answer each bullet point individually as its own paragraph. So let's just have a look at some of these answers, which a lot are just factual knowledge you've just got to learn for the course. So for the first bullet point is the idea that the highly radioactive nuclear waste is the fission fragments from the fission process, because what you tend to find is the fission fragments, the daughter nuclei produced, are actually going to be very radioactive themselves. So that is actually going to be the most dangerous part of the waste. Now the second part asks you to pretty much talk about what the process is for dealing with nuclear waste. So remember, the first thing is to put the waste in cooling ponds of water. That's for 2 reasons. Number one, it's to cool down the very hot nuclear fuel rods, but also to shield people around from any alpha particles given off by these particular these rods. Then the plutonium and uranium is separated in a reprocessing plant and then is recycled into further fuel rods. The high level waste left behind after this process is then vitrified, so it's made into solid glass, and then it's placed into stainless steel or lead or concrete cylinders and bunkers, which are stored deep underground. So it's very, very important that you say it's deep underground, and in the UK it's monitored very carefully as well. Now the last question, if you notice, asks you to talk about problems faced with dealing the waste and how we overcome it. So let's think about what the case is. So like mentioned before, the waste produced is initially very hot after the fission process, and so it has to be placed in water or cooling ponds to cool down, and it's also very radioactive, so there the water is also used to shield people from this dangerous radioactivity being given off by the waste. The waste also, if it's in a liquid form, can leak into the surroundings and get into our food chain and our water supply, which is not ideal, as you can imagine. So we vitrify the face, we turn it into glass, so that means that it can't actually leak out and it can't get into our food supply, our food chain, or our water supply. Now another issue is that the waste will be radioactive for hundreds and hundreds of years, or even thousands of years. So we need to store this waste in a stable situation so it isn't actually then knocked out or then put into the food chain or the water supply at a later date. So we need to store them in geologically stable areas, not areas which undergo earthquakes or have volcanoes. And finally, the last thing is the idea that transporting the waste can present a danger to the public, so you make sure you've got to have it enclosed, so even if there is a crash, then the waste will not leak out and people could be contaminated by the waste. Right, the next question says, calculate the binder energy in MeV of a nucleus of 5927 cobalt. You are given the nuclear mass in U. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, what you've got to do is you've got to work out the mass defect of the situation. So what we know is that we know the nuclear mass of cobalt itself, because it's given in the question. Now we can also work out what our value is going to be when we're just considering the nucleus in its separate components. Now we're told in the question, now we've got 27 protons there and we've got 59 nucleons. That tells us we must have 32 neutrons in the nucleus. Now you can find the mass value, the nuclear mass in U for the proton and the neutron in your equation booklet, so it isn't given in the question. So what you do is you work out the total the total mass of all the protons in the nucleus, you work out the mass of all the neutrons in the nucleus, you then subtract that total value by adding the two from the nuclear mass that's stated in the question. This will give you your mass defect. This will give you the mass change from turning your protons and neutrons into the nucleus, and then you can work out your binding energy by multiplying that value by 931.5, because that's the conversion factor between U in the mass in U and the energy in MeV. So you should work it out to be that the mass difference in U is 0.5408, and you multiply 931.5 to get your value of 503 MeV. The next question says, a nucleus of iron 59 decays into a stable nucleus of cobalt 59. It decays by beta minus emission, followed by the emission of gamma radiation as the cobalt 59 nucleus de-excites into its ground state. The total energy released when the iron 59 nucleus decays is 2.52 times 10 to the minus 13 joules. The iron nucleus can decay to one of three excited states, so that the cobalt 59 nucleus, as shown in the figure 5. The energy of the excited states are shown relative to the ground state. Calculate the maximum kinetic energy in MeV of the beta minus particle emitted when the iron 59 nucleus decays into an excited state that has an energy above the ground state. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? So you'll note straight away that how much of the total energy is released. It's 2.52 times 10 to the minus 13 joules. You are given that in the question. Now you also note that you've got a value of what it would go to, okay, by beta minus, okay, into an excited state that has the energy above the ground state. So if you look on your diagram, the ground state is 0, so the energy above the ground state is going to be 1.76 times 10 to the minus 13. Now, why don't you use one of the other two? Well, you don't, because it's asking for the maximum kinetic energy, so that's going to be the biggest difference. So the other two values will not give the biggest difference because they are bigger values. So you do 2.52 times 10 to the minus 13 minus 1.76 times 10 to the minus 13, so therefore you would get 7.6 times 10 to the minus 14 joules. Now the question wants it in MeV, so you've got to go backwards and convert it back into MeV, and remember 1 MeV is equal to 1.6 times 10 to the minus 13, so you divide it by that value to get 0.48 MeV. The next question says, following the production of the excited states of 59 cobalt, gamma radiation of discrete wavelengths is emitted. State the maximum number of discrete wavelengths that could be emitted, and then calculate the longest wavelength of the emitted gamma radiation. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, how do you work out the maximum number of discrete wavelengths? Well, it's equal to the number of differences between the actual energy levels. So what you would do is you would go from energy level 1 to ground state, energy level 2 to ground state, energy level 3 to ground state, then you'd have energy level 3 to energy level 2, energy level 3 to energy level 1, and energy level 2 to energy level 1, all the possible differences. So when you count up all those values, the number of possible differences is 6, so you would get 6 wavelengths, because each wavelength is related to a difference between two of the energy levels given in the diagram. Now calculate the longest wavelength. Now it's important that you remember that C is equal to F lambda. So this tells us that for this particular idea that the longest wavelength is actually linked to the lowest frequency, because when wavelength goes up, frequency goes down, and frequency links to energy. So therefore the smallest energy is going to be the lowest frequency, so therefore the longest wavelength. So what you would do is you would work out the smallest difference fundamentally, so that is from 2.29 to 2.06, that's the smallest difference you can get between any of the values, times by 10 to the minus 13, because it's times 10 to the minus 13 joules. That gives you your smallest energy difference, so therefore we can say lambda is equal to hc over E. We know h, it's Planck's constant, you're given that on the equation booklet. You know c, it's the speed of light, 3 times 10 to the 8, you're given that on the equation booklet. You pop in your smallest difference of energy, and you get your longest wavelength, which is 8.7 times 10 to the minus 12 meters. The next question says, the age of the moon has been estimated from rock samples containing rubidium and strontium brought back from the moon landings. Rubidium 8737 decays to strontium 8738 with a radioactive decay constant of 1.42 times 10 to the minus 11 per year. So calculate in years the half-life of rubidium. So pause the video now, then unpause the video when you want to go through your answer. Right, for this question, think about what you've been given. You've been given the decay constant and you need to work out the half-life. So if you look at your equation book, you'll notice that half-life is equal to log 2 over the decay constant. So we know log 2 is 0.693. We're given the half-life per year in the question, so you pop the values in and you get your answer to be 4.9 times 10 to the 10 years. The next question says, a sample of moon rock contains 1.23 milligrams of rubidium. Calculate the mass in grams of rubidium that the rock sample contained when it was formed 4.47 times 10 to 9 years ago. Give your answer to the appropriate number of sig figs, and then calculate the activity of a sample of 8737 rubidium of mass 1.23 milligrams, give an appropriate unit for your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this one, you'll notice in the question you have a value for time, okay, and you need to work out mass. So you can use the equation m is equal to m0 e to the power minus lambda t. So again, how can you work out lambda t? Well, in the previous question, you had the decay constant. Now, and then you can also got the time in this particular question because it tells you 4.47 times 10 to 9 years ago. So you've got your decay constant, which works it through to get out your value of lambda t like that. You know what your value of m0 is because it tells you it starts off with 1.23 milligrams. So that's 1.23 times 10 to the minus 3. So at that point, you can pop all the values through and you can work your answer out to be 1.31 times 10 to the minus 3 grams. Now again, how many sig figs do you put your question to? Well, you give it to 3 sig figs because all of the values given in the question are given to 3 significant figures. Now the next one is ask you to calculate the activity. So what you got to remember is that we know that n is equal to 8.5 times 10 to the 18. Now you can think about where that comes from, because it's going to be the mass, okay, and linking it into dividing by 87u, because you can think about where, how your mass is going to be your value of n times by 87u, so you can work it out like that. You are given n in the question, which is the number of, which is, if you think about it, it's going to be the number of atoms which are present. So at that point you work it through, and then you can say a is equal to lambda n. You've already got lambda from the previous question, so therefore you can work out a by popping all the values in to be 3.8, and then what's the units? Well, it's activity, so the units of activity per second are going to be becquerels. The next question says, a nucleus of polonium PO may decay to the stable isotope of lead 20882M and then through a chain of emissions through the sequence of alpha, beta minus, alpha. Figure 13 shows the position of the isotope 20882 lead on a grid of neutron number n against proton number z. Draw 4 arrows on figure 13 to show the sequence of changes to n and z that occur as the polonium nucleus is transformed into 20882 Pb. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you've got to remember is, in these types of graph, what's the change to the neutron number and what's the change to the proton number in alpha decay and beta decay. So in alpha decay, because you're losing 2 protons, 2 neutrons, in those instances the number of the neutron is going to go down by 2, and the number of the proton is going to go down by 2. Now you'll notice that the position on the graph you're given is the one at the end, so we're going to have to work backwards in essence. So we're going alpha and we're going back up like that because it's after the decay, so we're working backwards. So you've got your alpha like that. Now in beta minus, what's actually happening? Well, in beta minus decay, what do we know? Well, in beta minus decay, we know that a neutron is turning into a proton plus a beta particle and an antineutrino, but that's irrelevant for this particular question. So we can say that if a neutron is turning into a proton in beta decay, then therefore the neutron number goes down by 1, the proton number goes up by 1. So you can see it in the diagram there. Now the next question says, a nucleus of the stable isotope 20882 lead has more neutrons than protons. Explain why there is an imbalance between the proton and neutron number by referring to the forces that operate within the nucleus. Your explanation should include the range of forces in which particles are affected by those forces. So pause the video now, then unpause the video when you want to go through your answer. Right, now this question is really linking to stuff you did in particles, but it's asking about why you get stability in the nucleus between the protons and the neutrons. So it's the idea that the interaction involved is the strong nuclear force, and that affects protons and neutrons. It affects anything made from quarks, so it'll affect all your nucleons. Now your strong nuclear force has an attraction up to about 3 or 4 femtometers, but it's repulsive below about 0.8 1 femtometer. Now electromagnetic repulsion will only act between the protons because they're charged and the neutrons are not, but the electromagnetic force has an infinite range and acts across the whole nucleus. So what the idea is that you need more neutrons to hold the nucleus together, because what they will do is they will increase your strong nuclear force because they will experience that, but will not experience the repulsive electromagnetic interaction, so will therefore hold it together in a more stable fashion. So it's important to note that the more neutrons will make it more stable. So what does that mean? It means that the binding energy per nucleon has increased, because binding energy per nucleon is a measure of nuclear stability. Let's now have a look at some questions on magnetic fields. So the first question says, figure 8 shows a step-down transformer used in a laptop power supply. Firstly, explain the purpose of the core in the transformer. Then describe and explain 2 features of the core that improves the efficiency of the transformer. Then explain why transformers only work continuously when supplied with an alternating current. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So in the first one, you've got to understand what the core of the transformer is. So the core is there to ensure that the linkage from the primary coil is interacting with the linkage of the secondary coil. So the core is there to focus, direct, guide the magnetic field round from the primary to the secondary. So it's making sure that you got your flux from the primary coil linking to the flux of the secondary coil. Now, what two features of the core will improve the efficiency of the transformer? Well, there's actually three. The first one is you make your core out of soft iron, because this allows the magnetic field of the core to alternate easily, because if it struggles to alternate as they've got your alternating current passing through it, you will get hysteresis and energy will be lost out of the core. Another thing is you want to reduce eddy currents that are induced in the opposite direction in the core due to Lenz's law. So what you would do is you would laminate the core, which is pretty much mean cover in an insulator. So even though you'd have the same change in the magnetic field and you'd have that same potential, well, that same EMF induced, the current will be lower because the resistivity in the actual core is higher. And then finally, the same thing was mentioned before, you can make it out of a high resistivity metal, so even though you've got the same induced EMF, the actual eddy current produced is going to be less because it's a higher resistivity material. Now, explain why transformers work continuously only when supplied with an alternating current. Well, it's because an induced EMF is produced by a change in magnetic flux linkage. That is Faraday's law. So the alternating current will produce a change in magnetic flux linkage because it is going, the alternating current produces a magnetic field that goes backwards and forwards, so you get your change of flux in the core. The next question says a primary coil of the transformer is connected to a 230 V RMS AC supply. The current in the primary coil is 0.3 amps RMS and the secondary coil has 300 turns and provides an output of 20 V RMS and a power of 65 watts. Calculate the number of turns on the primary coil and calculate the efficiency of the transformer. So pause the video now, then unpause the video when you want to go through your answer. Right, in the first question, you've just got to use the transformer equation which is given to you in the equation booklet, and that is that MP over VP is equal to NS over VS, where P is the primary and S is the secondary. Now, you're given in the question NS, it tells you the number of turns on the secondary coil, 300. It tells you the potential difference or the voltage of the primary. It tells you that it's going to be 230, and we've also got the potential difference or voltage of the secondary. It tells you it's 20 from reading the question. So you pop all the values in and you work out to be 3,450 turns. Now the next question is looking at efficiency. Now you should be aware that efficiency is the useful power out over the total power in. Now it tells you in the question the useful power out, which is the power of the secondary, because the secondary is the output of the transformer. It tells you 65 watts in the question. Now you can work out the input power, the power in the primary coils, because you know that P equals VI. You've got V is 230 from the question, I is 0.3 from the question, so it'll be 230 times by 0.3 to give you your power in, so you work it out to be 0.94. The next question says a cyclotron has two D-shaped regions where the magnetic flux density is constant. The D-shaped regions are separated by a small gap. An alternating electrical field between the D-shaped regions accelerates charged particles. The magnetic field causes the charged particles to follow a circular path. So derive an expression to show the time taken by a proton to travel around one semicircular path is independent of the radius of the path, and that the maximum radius of the path followed by a proton is 0.55 meters, and the magnetic flux density of the uniform field is 0.44 teslas. Calculate the maximum speed of a proton that leaves the cyclotron. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to prove mathematically that pretty much that T does not include R in the equation. Now, when you've got this particular setup, you know that the centripetal force in this example is the magnetic force, because the magnetic force is acting perpendicular to motion, so it has to be the centripetal force. So we can say that the general centripetal force equation is mv squared over r. We know that the equation for the magnetic force on a charged particle is bqv, so we can straight away equate the two. Now we can say that the time in the semicircle, which is what we need to think about for this particular equation, is distance over speed, because speed is distance over time, so we just rearranged it. Now the distance covered in a semicircle is pi r, because it's half the circumference, and the circumference is pi d, and r is half of d, so therefore the distance of the semicircle is pi r. So what we can say is that t equals pi r over v. Now we've got r from our equation bqv equals mv squared over r, so we can substitute that value in and then make r the subject and put time in the equation. We can then rearrange it all and get that the time in the semicircle is going to be equal to pi m over bq. Now you'll notice in this situation r is not present, so therefore it must be independent of each other. Now, what you can do for the second question is once again say BQV equals mv squared over r. Why can we do that? Because in this example, the magnetic force is acting as the centripetal force. We can rearrange it and we can make v the subject. So we can say from our equation that v equals BQR over m, because we just cancelled out some terms and made v the subject. You've got b in the question, it's 0.44. You've got q, because you know it is a proton, so the charge is 1.6 times 10 to the minus 19. That's just a fact you've got to know. And we know r from the question is 0.55, and we know that if we look at that mass of the proton, you're given it in the equation book, 1.67 times 10 to the minus 27 kilograms, so you get our answer to be 2.3 times 10 to the 7. The next question says, state Lenz's law. Then Lenz's law can be demonstrated using a bar magnet and a coil of wire connected to a sensitive ammeter as shown. The bar magnet moves towards the coil and is then brought to a halt. State how the reading on the ammeter changes during this process. Then during the demonstration, an induced current is detected by the ammeter. The induced current is in the direction E to F. Explain how this demonstrates Lenz's law. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first one is just a fact. You've just got to learn Lenz's law, and that is that the direction of the induced EMF, which is produced with the change in flux linkage, is going to oppose the change in flux linkage that is producing it. The magnitude law is Faraday's law, the direction law is Lenz's law. Now in this next question, we can use this idea to actually understand from Faraday's law what's actually happening to the reading on the ammeter. And what happens in this process is that there will be a reading on the ammeter when the magnet is moving towards the coil, because when it's moving towards the coil, it's changing how many field lines it cuts through. Well, the coil cuts through because the magnet's changing how close it is to the coil, so therefore there's a change in magnetic flux linkage, so therefore there will be an induced EMF and therefore a current produced in the circuit. However, when the magnet stops moving, whilst there's still a flux linkage because the coil is still in the magnetic field of the bar magnet, there's no longer a change in flux linkage because it's not changing, because everything's staying stationary, so there's no induced EMF, there's no current, and there's no reading on the ammeter. Now it says during the demonstration, the induced current is detected by the ammeter, and the induced current is in the direction E to F. Explain us how this demonstrates Lenz's law. Well, if you think about it, the induced current is going to produce a north pole on the right hand side of the coil, if you think about what's going on, which is going to oppose the motion of the magnet, and you'll get that repulsive effect. Now this is important because it tries to maintain a small magnetic field as the magnet approaches the coil, so it indicates the idea of Lenz's law. So let's have a look now at a few questions on gravitational fields. So the first question says, define the gravitational potential at a point and then explain why gravitational potential is always a negative. So pause the video now, then unpause the video when you want to go through your answer. Right, the first two questions are just literal definitions you've just got to learn. So gravitational potential, and this is a 2-mark definition, is the work done per unit mass, because gravitational fields are always per unit mass, in moving the massive object from infinity, from outside the field, to a point inside the field. Now, why is gravitational potential always negative? It's because we define gravitational potential to be 0 at infinity. So outside of the field, the energy that the object has per unit mass is 0. Now, that tells us we've got to put work in when the object's in the field to get out of the field, because gravity is always an attractive force, so we've got to put energy into it for the object to get out of the field. So if we're putting energy in to reach 0, it must start off as a negative value. The next question says, show that the magnitude of the gravitational potential at the Earth's surface due to the mass of the Earth is about 6.3 times 10 to the 7 joules per kilogram. Then a satellite is launched into a geostationary orbit. Describe and explain two features of a geostationary orbit. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got to look at our equation for gravitational potential, which is found in our equation booklet. And that is V, gravitational potential, is equal to minus big G, big M over R. Now, big M is the mass of the object producing the field, which is the Earth. And you're given the mass in this particular question. So we know that the mass of the Earth, okay, is going to be 5.97 times 10 to the 24. We know this because it's given to us in our equation book. We know what the value of R is. It's going to be 6.37 times 10 to the 6, because that's the radius of the Earth, because we're going from the center of the Earth to the surface of the Earth. Once again, the radius of the Earth is given to you on your equation booklet. And we know what big G is. It's 6.67 times 10 to the minus 11. Once again, that number is given to you in your examination book. So it works out to be minus 6.25 times 10 to the 7 joules per kilogram. Now the next question is just asking for some facts about geostationary orbits which you've got to memorise. So a geostationary orbit is in the plane of the equator, it's always above the same location on the Earth, and they have the same time period as the time it takes for the Earth itself to rotate, because it's always above the same point on the Earth. It's always 24 hours above it. The next question says, the satellite has a mass of 1,200 kilograms and it has a radius of its orbit of 4.23 times 10 to the 7 meters. Calculate the gain in gravitational potential energy of the satellite when it's placed in orbit from the Earth's surface, and then impulse engines are used to place the satellite into an orbit with a longer period. Discuss any changes this may make to the orbital motion of the satellite. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to remember gravitational potential energy is equal to the change in potential times by the mass of the object. That's just a fact, that potential energy is the change in the potential multiplied by the mass. So what do? We work out our potential. We've already worked out our potential at the surface of the Earth from the previous question. So let's now work out the potential in this new position in orbit above the Earth's surface. So now we say V equals minus Gm over R. Big G is just a number like before. The mass of the Earth remains constant. However, now the radius has changed, because what we've got to do is we've got to add 4.23 times 10 to the 7 in there. So it's now 4.23 times 10 to the 7 as our value of R. So therefore what we get is our value now is 9.41 times 10 to the 6 joules per kilogram. We then say potential energy is the change in potential, so it's the difference we just had from the previous one and now our new value, multiplied by the mass. And we know the mass of the satellite, small m, because small m is the object that's not making a gravitational field, it's just in it. So it's 1,200, so we get our answer to be 6.38 times 10 to the 10 joules. Now in our next question, discuss any changes using impulse satellite engines will do to put a satellite into an orbit with a longer period. So if we put it into a longer period, we've got to be aware from our equation of orbiting bodies that r cubed is proportional to t squared. So this tells us that when it's put into a longer period, if t has increased, so therefore t squared has increased, well therefore r cubed has to increase because they're in proportion to each other, so therefore the radius will increase. But also we know from circular motion that what's the link between time, okay, and speed, or we could say radius and speed. So we know that, well, mv squared over r, so that tells us therefore that v squared is proportional to 1 over r, because that entire term mv squared over r has to equal the same force, the same centripetal force. So v squared is proportional to 1 over r. So therefore when the time period, sorry, when the radius increases, which we just worked out from our idea of r squared is r cubed, so it's proportional to t squared, well therefore that tells us that v is going to get smaller as well. The next question says, state what's represented by gravitational field lines. Then figure 6 shows the gravitational field above a small horizontal region on the surface of the Earth. Explain why the lines converge over a small area at K. Then a ball travelling at a constant speed passes position J, moving towards position K in the figure. Explain any changes in speed of the ball as it approaches K. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first one, again, is just a fact you've got to learn. Gravitational field lines show the direction that of the force on a mass. So it's the direction that a stationary mass or unit mass will move in a situation. Now you've got to think, why would the field lines converge over a small area? Well, the separation of the field line density is a link into the field strength. So therefore it tells us that the gravitational field around K is going to be stronger. Now it's either going to be because there's more mass in around K, so therefore you're going to have a greater gravitational field, or also that the density is going to just be bigger at around that point, which is more likely. So the answer is more likely to be that at K, that the rocks are denser, so therefore you've got a higher proportion of mass per unit volume, so therefore your gravitational field will be stronger and bigger. Now what's going to happen to the speed of the ball as it approaches K? Well, you'll notice that as the object approaches K, there's a stronger gravitational field, so there's a stronger attraction there, so the ball will speed up, it will accelerate as it moves towards K. Now again, you can see this because the potential is going to be lower at K, so therefore it'll want to get there, it'll want to accelerate towards it. The next question says, derive an expression to show that for satellites in a circular orbit, t squared is directly proportional to r cubed, and then Pluto is a dwarf planet. The mean orbital radius of Pluto around the Sun is 5.91 times 10 to the 9 kilometers, compared to a mean orbital radius of 1.50 times 10 to the 8 kilometers for the Earth. Calculate in the years the orbital period of Pluto. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, what you've always got to remember is that if an object's going in a circular orbit, well, therefore you've got a centripetal force acting on the object. And then we know in this case, because it's orbiting due to gravity, that the gravitational force is going to be the centripetal force. So we can say that mr omega squared, which is our centripetal force equation, it's just a link to mv squared over r, but with omega instead of v there, is going to be equal to g big M small m over r squared. We can then equate the two to each other. We can therefore then link it into the idea of t by understanding what t is, and that is that, well, omega is equal to 2 pi f. So we know that f is 1 over t, so therefore omega is equal to 2 pi over t. So when we say mr omega squared, we can actually write that as mr 4 pi squared over t squared. We can then rearrange it all and make t squared the subject, and we get out that t squared is equal to 4 pi squared over gm times by r cubed. Now 4 pi squared is a constant, gm is a constant, so that leaves us that the only two values that can change in the situation is t squared and r cubed, so they must be directly proportional to each other. Now the next question, if we know that t squared is directly proportional to r cubed, well, we can use that in our proportionality. So we can say that t1 over t2 all squared is equal to r1 over r2 all cubed, because they're just directly proportional to each other. Now we're given in the question the time period of the Earth, because we know it to be 1 year. Now you think, why we're using years in this question and not seconds? Well, we're doing that because it's a ratio, because it's t1 over t2 and r1 over r2. So as long as we keep it the same units, it should work through. So we know that the time period of the Earth is 1 year. We've got the radius of the orbit for Pluto, the radius of orbit for the Earth in the question. You can then make the orbital time period for Pluto to be the subject, and you work it through to be 250 years. The next question says, a small mass released from rest just above the surface of Pluto has an acceleration of 0.617 meters per second squared. Assume that Pluto has no atmosphere that can provide any resistance to motion. Calculate the mass of Pluto to an appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? Well, what we can say is we know what we need to work out the mass of Pluto. Now it says a small mass is released, so what we can say is we can say that F is equal to G big M, which is the mass of Pluto, the mass of the thing producing a gravitational field, times by small m, the mass of the small mass, divided by r squared. What we can then do is we can rearrange it and make it the subject by saying that big M, the mass of Pluto, is gr squared over g, big G, like that, because now we've linked it into the acceleration due to gravity. So we can link it through like that, where we can say small g is the acceleration. So we can say that, well, acceleration due to gravity, gravitational field strength, is gm over r squared. So we've now made big M the subject and pop our values in to be 1.31 times 10 to the 22 kilograms. Now again, how many significant figures do you give it to? Well, 0.617 is 3 sig figs, because you don't count the first zero. 1.19 times 10 to the 6 is 3 significant figures, so your answer should be to 3 significant figures. Our next question says, figure 8 shows the variation in gravitational potential with distance from the centre of Pluto for points at and above its surface. A meteorite hits Pluto and ejects a lump of ice from the surface that travels vertically at an initial speed of 1,400 meters per second. Determine whether this lump of ice can escape from Pluto. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, there's a few different ways to answer this particular question. However, how I would tend to do it is I would work out the escape velocity of the situation. Now you can work out the escape velocity because what you can do is you can say at the escape velocity we can say that the kinetic energy is going to equal the gravitational potential energy. So we can eventually work out the escape velocity. We say half mv squared equals to gmm over r squared. We can work it out to say eventually that v is equal to the square root of 2gm over r. Now we know m, which is the mass of Pluto from the previous question. So we've got big M, we know big G, and we know what the distance from the centre of Pluto is going to be by looking at figure 8. So you can work out what our distance from the centre of Pluto is going to be. So therefore you can work out your escape velocity, and therefore you can work out your escape velocity is 1,200 meters per second. So that's our minimum velocity needed to escape. We're told it's leaving with 1,400, so therefore it's at a value bigger than the escape velocity, so it will leave the field. Another way you could do it is you could work out the initial kinetic energy of the object that's been ejected by doing a half mv squared. We can then work out the energy needed to escape, because you'll notice from our figure 8 we've got our gravitational potential, so we know what that value is. So therefore we can link that in by saying, well, the gravitational potential energy is going to be the mass times by the change of potential. So you can see how the potential changes when it's going from 1 times 10 to the 6 to 6 times 10 to the 6. So you can see how the potential changes. You can multiply it by your mass, which is, you can work it through like so, and then you can see what it's got enough energy to escape by comparing the kinetic energy to the energy needed to escape. So I hope you've enjoyed this particular revision session, and this revision session has been successful. So if it's been successful and you've learned in this revision session, you should be able to answer A-level physics examination style questions, assess your understanding on A-level physics, and finally understand what topics you need to improve upon for A-level physics. Thank you very much for watching this particular revision session on paper 2 for AQA A-level physics. Thank you very much for watching, and have a lovely day.